Hello, Bertrand.
Hi, Nishant.
Hi, yeah, could you turn on the video? Nice to see you.
Yeah, nice to see you too.
Yeah.
Sorry. Yeah.
Nagaya, it is the same website, right? No, the link is same. Hello.
Yeah, sir, we can hear you. This is the same website. Yeah,
Same website, right?
yeah, yes, sir. Yeah.
Am I okay? Yeah.
Yes.
Okay, good. Okay, I have it here.
Good afternoon, Krishnamurthy.
Good afternoon, Krishnamurthy.
So should we start, sir?
We still have time, no? Because don't give me 10 minutes. What do I have to?
Yeah, it's almost 3:70 now. So
Oh, it's okay. Just okay. Give us another 2-3 minutes. Let the people join.
sure.
You have the speaker, right?
Yes, sir.
The first speaker is from Professor, I think it's Kaust, no? From Kaust, isn't it?
Sure. Yes, sir.
Correct. Yeah, I'm here.
Yeah, okay.
Pleased to meet you. And
Yeah, nice
congratulations.
to see you too. Yeah,
Thank you.
wonderful. I think you're, yeah, Professor Keys, very nice to see you.
Thank you, sir.
Yes, Murthy.
Honor.
Sir, we also have Bertrand Laurent from France.
Oh, wonderful.
Yeah,
Wonderful.
Bertrand.
And I see that Peter Bastien is on.
Hello. There's Murthy. From ICT. I think all of you, I welcome all of you to our campus. It's a beautiful campus, and I'm sure in times to come, you will be here with us. Right?
Indeed. I've been to Trivandrum once,
Oh,
to the
okay.
ISRO, to the Satellite Launch Center.
Okay. Yeah, but we are in a hill station almost at the, I don't say hill station, at the feet of the hills, Western Ghats.
Uh-huh.
It's in a beautiful setting. It's picturesque, in fact.
Nice.
Kerala as such is really beautiful, but I think I would say we are in a place that is much more beautiful.
Huh.
Yeah. Yes, Nagaya, I think we can start now.
Okay. Yeah. So distinguished professors, honorable director, and valued colleagues, participants, and students. On behalf of organizing committee, a warm and respectable welcome for the first international workshop on high performance computing in science and engineering. Myself, I'm Nagaya Chamakuri from School of Mathematics, IISER Thiruvananthapuram, and I am one of the organizers of the workshop. We are indeed grateful to all invited speakers for graciously and readily accepting our invitation. We have 6 keynote presentations from renowned speakers around the globe. Professor David Case from KAUST and Columbia University, USA. Professor Peter Bastian, University of Heidelberg, Germany. Professor Eduardo Di Napoli, Ulysses Supercomputer Center, Germany. Professor Bertrand Laurent, CNRS, France. Professor Heather J. Kulik, MIT, USA. Professor Martin Head Gordon, University of California, USA. We are honored to have you here with us. And moreover, we have 284 registered participants. Now I would like to welcome the chief guest, our Honorable Director, Professor Jayan Murthy, to give the inaugural speech. So please put your hands together for a warm welcome for Professor Jayan Murthy.
I think we should welcome our guests, not me, because we are the hosts, right? I think all of you should join me in welcoming Professor Kais and Bertrand Laurenti from France. It's indeed wonderful. Very good afternoon and good morning to the participants from India and from outside. Well, high performance computing, in fact, is not something that I started. I think the credit goes to the previous administration. I believe some of our colleagues in the campus, I think it is for the benefit of all the participants. I would like to say a few words about IISER Thiruvananthapuram. It's by going by the very name. It's a science education, Institute for Science Education and Research. We have 4 disciplines, namely chemistry, mathematics, physics, and biology. And last year we added data science. So which makes it to 5. Of course, we are in the kind of expansion mode, and years to come, and I'm sure the institute will swell. Otherwise, this is an institution which was founded in 2008. Already it's into about it's the 14th year. So it's rooted in sciences and mathematics, our institute. And I believe some practitioners basically got together, submitted a huge proposal to Department of Science and Technology of India, got some funding, and the institute supported to some degree. And that is how we have gotten this exotic facility in our campus, spending a lot of money. In fact, it has been since about a year that we have commissioned this HPC. I think Dr. Nagaya is a coordinator, convener of this HPC, and there is a team of users, right? And we believe, we all know that. I think in the present day, scientific innovations cannot be possible without computational power. And I am a practicing chemist, particularly an organic chemist, and I'm not a theoretician. But otherwise, we keep hearing about what computations can do, be it chemistry as applied to some kind of ab initio, structure determinations or structure calculations, and as applied to in biology, computational biology, where we speak about proteomics, genomics, and bioinformatics and whatnot. And if you get into the physics realm, I think it's a very hard, basically quantum technologies, computational quantum technologies, astrophysics, physics data, which is to do with processing every information about even, for example, the climate change. I think the applications, let us accept, are vast. And in fact, data science or, the computations is all about computations, high performance computations. You be it in mathematical sense as applied to the phenomenon that we have seen. We have seen in Indian context itself a lot of models to predict as to when this prevailing pandemic will get past. In other words, I'm not to talk about the importance of the HPC. I think going by the very objective that has been spelled out very clearly in the brochure, it's all about basically bringing together different communities that are discretely functioning together and look at the current challenges that we are faced with and target larger picture. I think that is the purpose. So right now it is just a center, and the way that I envisage this center really sort of expanding in times to come is to sort of bring in people that are working in disparate areas and sort of make them adjunct professors of this center, allow the possibility of even the students being registered for PhD, foster with time to come international cooperations, right? And also sort of nurture the international eminent people to come to the campus and spend their time here as visiting professors and give some lectures and facilitate this computational science to grow. In fact, for the benefit of others, I would like to say that last year we started what are called as I Square Sciences, brand new, to mean integrated and interdisciplinary sciences. I think our vision is that these new programs that are 5-year programs build on the core content in sciences and mathematics and sort of expand into the challenges of today, and which is how basically the data science basically comes into picture. I think the computations become integrally a very important, the component in the overall curriculum development. So given that, it's only, I would say, a beginning for what is due to come in years to come in IISER Thiruvananthapuram. Right? The data science, we are in fact looking for faculty to be hired as part of the data science program. And in the coming years, and we would like to see this data science discipline basically have about 8 to 10 faculty with expertise in the domain, in the same domain, right? So HPC becomes essentially part of this with time to come, and all the practitioners can be associated with it, right? I think the avenues are a lot, and I think my colleagues told me the computations are there everywhere. I think in the workshop that is being organized now, we have speakers, eminent speakers, to talk about in the today and tomorrow as applied to computations, as applied to chemistry, physics, mathematics, and biology, the subjects that we practice here. I think they're really eminent, and I would like to sort of express my gratitude to the speakers for accepting to give talks as part of these workshops. With that, I think I should not be taking too much of time. It's indeed a pleasure, and I sincerely wish that the workshop will be a grand success, and there'll be a lot for people, particularly the practitioners in our campus and all the people that are coming from other parts of the country to learn a lot today and tomorrow. I wish the workshop a grand success. Thank you very much. Yeah.
Thank you, sir. Thank you very much for your great support and encouraging words. Now we will move to the technical sessions. So Professor David, so if you don't mind, can you share the slides?
I hope they're visible now.
Yes, perfect.
Okay. Well,
Yeah, so sorry for everyone. So there is a small problem with the internet, the web services. So our website is not accessible from outside of IISER network. So I will try to post the program here itself, but otherwise it's okay. So first, it's my great pleasure for me to introduce our inaugural speaker today, Professor David Case. He's a professor from KAUST, and he remains an adjunct professor at Columbia University, USA. So he's very well known in the domain decomposition community, and no need introduction, but I will give a short bio sketch of Professor David.
greetings.
He earned a
Paul.
BSc in, yes, sir. Sorry.
Oh, no, fine. I thought the introduction was over.
Yeah, so he earned a BSc in aerospace and mechanical sciences from Princeton and a PhD in applied mathematics from Harvard. Professor David Case directs the Extreme Computing Research Center at KAUST, where he has founding dean in 2009 and holds appointments in applied mathematics, computer science, and mechanical engineering. He is also adjunct professor at Columbia, where he formerly held the Fu Foundation Chair. He works at the interface between parallel computing and partial differential equations and statistics, with a current focus on exploiting data sparsity. He is a fellow of SIAM, AMS, and AAAS. He has been awarded the ACM Gordon Bell Prize, the IEEE Sydney Fenbach Award, and the SIAM Prize for Distinguished Service to the Profession. So we are privileged today to hear him speak on the scalable solvers for CSE. So please join me in welcoming Professor David Case. So I will now hand over to Professor David.
Okay. Well, thank you so much. And congratulations and best wishes on the inauguration of a new institute. It is certainly an honor and a privilege to set a tone with an inaugural lecture. And for it, I have chosen a topic that I hope has somewhat universal relevance, namely scalable solvers for computational science and engineering. I greet you from a 12-year-old university that grew up around a supercomputer, where more than half of the faculty groups, be they from climate or combustion or chemistry or whatever, use our Cray XC40 at scale, many of them, namely up to 200,000 cores, and are readying themselves to scale up for the next system. The goals for this talk are, in fact, to recruit more researchers to what I believe we could call a renaissance in scalable solvers, coming from, among other things, data sparsity, to recap the opportunity, in fact, not just the opportunity, but the imperatives from computer architecture, and to describe several universals that will, I believe, govern scalable computing into the indefinite future, show some current algorithmic developments that relate to these, and illustrate very briefly with a handful of examples from some of our favorite solvers. I'd like to use the analogy of a falcon, which doesn't fly to where the prey is, but rather to where the prey will be. If the falcon flew towards the target in pink here, it would be constantly turning its tangent line. But in fact, the falcon does calculus. It watches where the prey is flying, how fast, in what direction, and it flies to where it will be in the shortest amount of time. And so let's fly with the falcons to where computer architectures will be. In fact, our computer is named after a falcon, which is why I chose that analogy. It's a very popular animal in the Arabian Peninsula. Well, this is the first terascale system in the world. It was ASCII read at Sandia in 1997. In 1999, my group with NASA helped win shared in a Gordon Bell Prize on this system. But in 20 years, all the computational power that took up that basketball-sized machine room could fit in the palm of your hand. That's a 1 teraflops ARM chip. But the bigger story really is the fact that it was 3.5 orders of magnitude less energy consumptive per flop. And in fact, if we take that 4 more years to the present, we now have the NVIDIA A100 system, which is 20 times more powerful than that ARM system of 4 years ago, and 32,500 times more power efficient per flop than the first terascale system. So this is really a theme in making computers more available and more climate friendly, you could say. And it will have enormous implications on data motion, which is the most energy consumptive part of computing, no longer the flops themselves. So here are my 5 architectural imperatives. One should try to reside high on the memory hierarchy with the major data structures, whether they are matrices or grids or whatever, close to the processing elements. To rely as much as possible on single instruction, multiple data, or multiple thread batches of tasks at the fine scale where there's custom hardware. To reduce synchronization in frequency or in span. Too many of our algorithms have frequent global synchronization. To reduce the volume of communication in number or in total volume. And to exploit heterogeneity, some of these attractive new heterogeneous accelerators that are available, or heterogeneous memory, or heterogeneous networking elements, including now, in some cases, direct optical. Strategies in practice already for doing some of these are to exploit extra memory where possible to reduce communication volume, to perform extra local flops to require fewer global operations, to use higher order discretizations in order to manipulate fewer degrees of freedom, but with many more operations per degree of freedom, to adapt floating point precision to output accuracy requirements, which often means making do with lower precision than default double, and take more resilience into algorithm space out of hardware and systems space, not make them repair momentary failures, which is very energy and time consumptive, but build such recovery into the algorithms themselves. There are many additional strategies in progress. such as moving away from pre-scheduled loops and too many subroutine boundaries with synchronizations between them, to dynamic runtime systems based on directed acyclic graphs of the fundamental data dependencies, not over-ordering, to code to specialized backends for general users while presenting high-level APIs, to exploit data sparsity to meet the curse of dimensionality in big data with the blessing of low rank that's built into many of the physical causal systems that we deal with, to process more on the fly rather than storing all at once, especially large dense matrices that have to live in deep memory, and to co-design algorithms with hardware, which would include computing in the network or in memory where possible. So the exascale algorithmic agenda is to emphasize heterogeneity and hierarchy. Heterogeneity of devices is the new normal. Hierarchy in terms of data structure is the key to efficient representation and access of big data. And I'm delighted that Peter Bastien is following later on this program to discuss in more detail many aspects of hierarchy in the sense of multi-grid at least. We need to watch hardware opportunities from traditional fat CPUs to vectors to GPUs to TPUs and onward through FPGAs, neuromorphic and quantum, all of which are coming and could farm out significant parts of our computation to devices where they are more efficient. To use more kinds of memory, cache, high bandwidth, DRAM, NVRAM, and so forth, and to use more kinds of hardware channels, communication channels as they become available. And to think and to teach our students to think on two levels. The high level is how to find the thresholds that amortize the overheads for changing devices in heterogeneity or changing scales in hierarchy. And at the low level, of course, learning the fundamentals, how to express efficiently the use of this new hardware. And we need to gain hands-on experience and integration, ideally in a multidisciplinary team, such as the teams you are building in your new institute, so that everybody's specialized efforts can be part of something bigger that motivates the whole and brings visibility and sponsorship. So I'll concentrate on solvers, and we will refer in general to this list of 5 kinds of solvers. A linear solver is usually at the heart of everything. For example, least squares call on linear solvers, singular value and eigensolvers have linear solves. Nonlinear solvers have repeated linear solves with a Jacobian. Implicit time integration schemes have a nonlinear solver at every time step. Sensitivity analyzers and optimizers repeatedly run implicit problems to determine sensitivities and to optimize parameters. And we need to have these fundamental kernels in ways that offer tunable accuracy, time, and space trade-offs. We're good engineers, right? We need to exploit data sparsity where we can find that in the mathematics. We need to exploit a hierarchy of precisions as they become available and offer lower energy computing to adequate accuracy. We may sometimes require more flops, but still finish earlier because we have more concurrency rather than operating with an algorithm that does less flops, but has no way of spreading it out to all the cores that are available. And of course, we seek energy efficiency. Today, there are 2 universes that exist side by side, a brown field of flat memory, which is not a realistic model for today's computers, and a green field of hierarchical memory where hierarchical data structures will prosper. In every case, we have some fundamental nested loops, whether they're over the dimensions of a grid or over the rows and columns of a matrix or more in a tensor or whatever. But the key is not to have those indices run globally, but to structure the problem so that they run locally in very fast memory and still coordinate to give the correct results. Now, algorithms were once flat. This is the famous triply nested loop of the Cholesky decomposition for a symmetric system. That gives you your n cubed complexity, which we now want to reduce to order n log n in data sparse algorithms. Architectures were also once flat. Von Neumann's first computer segregated the memory from the arithmetic logical unit. This is his 1945 report. And to a large extent, we're still using that computer architecture, at least in our minds, if not in the hardware. And so we have to adapt now to more realistic hardware. Now, one hierarchy is not so bad. If we were humans managing complexity, we might prefer hierarchical algorithms on flat architectures where all data was equidistant, or we might be able to tolerate flat algorithms on the complexity of hierarchical architectures. But when we try to do both at the same time, we have a real intellectual challenge. We have to marshal irregular structures into uniform batches that play well on GPUs or vector architectures. We need to feed dynamic runtime queues, and we need to exploit hierarchical memory and heterogeneous accelerators on their own terms. If you have to choose, well, Philippe Twin made his choice. I would rather have today's algorithms on yesterday's computers than vice versa. We need the optimal algorithms. And it is work, however. And so to quote the architect Yale Pat, if we forbid lazy microarchitects and lazy compiler people, then we must insist on equal attention from the algorithm people, which I assume in this audience is most of us. Algorithms must span a widening gulf between ambitious applications, multi-scale, multi-physics, high fidelity, et cetera, and austere architectures where energy efficiency is a premium. And this requires adaptive algorithms, and it's a full employment program for everybody who is under my age, I would say. Hierarchical algorithms must address the attention between highly uniform single instruction, multiple threaded operations, which prefer regularity and predictability, versus the irregularity and adaptability in hierarchical algorithms with tree-like data structures and scale recurrence. So we have a lot of work in hierarchical algorithms, for example, in MATLAB, a lot of performance attentive work at the high end, but not enough, I would say, in the intersection of mapping those complex hierarchical algorithms onto the new hardware. And that, I would say, is an agenda that your institute could share. Because billions of dollars, euros, pounds, rupees, yen and yuan of open source scientific software investment worldwide hangs in the balance. You might be able to move it to exascale systems, but you'll only get petascale performance without this reworking of algorithms. And the required software is immense. It's model related, such as in this left-hand column. It's development related, compilers, simulators, debuggers, profilers. That has to scale to millions of cores as well. And it's production related. We have to authenticate, we have to visualize, we have to manage faults, and so forth. And high-end computers come with very little of this. Most of it is contributed by the user community, which means PhD theses to be written in our respective universities. And in my group, we worry about solvers and integrators, and I hope that many others are worrying about all these other tasks. This is some of the open source software that we've been creating and depositing at GitHub. ExaGeoStat is a data sparse covariance matrix max likelihood statistics package that has an R interface. Multi-objective adaptive optics is a control system for the micro mirrors in the world's largest land-based telescopes, such as this Subaru system of Japan in Hawaii, where on a mountaintop, there's not a lot of electrical power to spare to solve the huge least square systems that come into controlling those mirrors to correct for atmospheric turbulence, for example. The KAUST BLAS, which is a collection of BLAS for NVIDIA in particular, and now for NEC, and also for other new processors that outperform the vendor defaults in special cases, particularly by using batched operations. Our singular value decomposition, now part of Cray's LibSci, it does a lot more flops than traditional eigensolvers and singular value solvers by forking down a tree, but it can exploit concurrency that other diagonally chasing methods cannot. Jira is a fast mesh traversal system designed for many core architectures that is now part of Aramco's Exawave seismic inversion software. And on top of that, the multi-layer buffer system for the I/O of doing reverse time migration, which reloads data from a previous shot back in memory many times, and that has to be buffered. An analogy to prefetching in a two-layer system, but generalized now to many levels of memory. And some of these other ones we are still working on and finding more and more uses for. So what will exascale algorithms look like? We have to start with algorithms that are as close as possible to the optimal asymptotic order. If you want to print out the data of order n, then you're going to be at least order n. And can you solve the problem in only log n times more than that, as for example, with multi-level methods? There are many such optimal algorithms. They've been discovered roughly once a decade. The FFT in the 60s, multigrid in the 70s, multipole in the 80s, sparse grids in the 90s, hierarchically low rank matrices in the thousands. Randomized algorithms are now very hot in the 2010s. And each of these replace one or more powers of problem size n in an original deterministic method with a log n, or even in some cases, a constant, as in the rank of a matrix block. And I'm very excited to see what the next generation will bring forth in the 2020s. One of my recent students wrote in his thesis, "With great computational power comes great algorithmic responsibility." And that's if we want to exploit these new powerful systems at scale. So we're at a baton handoff between the flat bulk synchronous generation that has served computational science so well for the last 28, 29 years since the MPI standard was formed, to a new finer grained, energy aware way of computing. So let's look at these 15 universals with a couple of minutes each. That will fill up my remaining time. So reside high on the memory hierarchy, close to the processing elements. You're familiar, I trust, with the concept of a memory hierarchy, a small amount of very fast, expensive per byte memory in terms of registers going down to remote, say, tape archives. Very slow to access, but very cheap per byte and very large scale. Even going from registers to DRAM or HBM these days costs about 100 to 1,000 cycles that could be used for operations. So we really have to operate at a higher level than that. And this is a picture of a prototypical high-end node on a supercomputer today, where there are thin cores, accelerators, for example, fat cores, your traditional x86, memory hiding kind of core, and then different kinds of memory on the chip or immediately off of it. John McAlpin has been tracking the worsening ratio of flops per byte access for 30 years. And notice the left-hand axis here is a log axis. And on various hardware architectures over the past 30 years, in green, the memory bandwidth, the increase of flops capacity divided by memory bandwidth, that has been growing at 15% per year. In purple, the local memory latency, which has been getting worse at about 20% per year compared to clock speeds. And in orange and in red, the off-node communication-related bandwidth and latency. All of these have been worsening at a rate of somewhere between 15 and 25% per year for decades, leading to great algorithmic imbalance where we are often memory starved. And that's just for a single core. Nowadays, our nodes have many core. And so if you replot the purple line from the previous against the local, the memory starvation for many cores per chip, it gets even worse. It's worsening at about 50% per year, largely because of the large number of cores that are becoming available because they're so cheap compared to everything else. Karen Bergman at Columbia has been tracking for the top 10 systems on the top 500, their memory bandwidth trends for the past decade. And you can see in green, the node compute power on average over the top 10 systems. It has risen by a factor of 137, whereas the node bandwidth has risen by a factor only of 6. So that ratio has worsened by a factor of more than 20. And this is just within the top 10. It's worse at the bottom, where less money is invested in fast memory. Of course, Fugaku, the latest system in Japan, has a step up in this, but that's $1 billion system. And most of us have to be content with more commodity memory parts. So why is EXA so hard? Why is this getting so much worse as we scale down in device size by, let's say, a factor of kappa, which means that our voltage per operation goes down by that factor while we maintain constant power density. This is the magic of Dennard scaling, which went on for decades after Dennard invented it for memory at IBM. But now we still have that scaling in the silicon, but unfortunately in the copper, we pay the price for shrinking in terms of memory dissipation on the via lines. And so this is why eventually our fast processing becomes limited by transmission loss or by a voltage threshold, making it harder to distinguish between signal and noise. We've seen this coming for 4 decades. It came, and now we have to cope with it algorithmically. So this is a chart from John Schalf showing the approximate cost of a double precision floating point multiply add at about 100 picojoules versus the cost of moving a single double precision word across the chip or the entire system, which can be up to 100 times worse than that. So remember, a pico looks small, but if you do it exa times a second, that's mega somethings per second. So we're talking about megajoules per second, and a 1 megawatt year costs about $1 million in many countries. So we're talking about enormous operation costs and costs to the climate. 100 megawatts for a exascale computer would be the equivalent of about 71,000 people in an OECD country. So we can't move that much data. We have to live high in memory hierarchy. What about the heterogeneity of SIMT chips? Well, we now have these tensor cores where in one single instruction, you can do 64 floating point multiply adds. You can multiply together 2 4x4 matrices and add them to a third. And this is an amazing operation if you can use it, which of course you can in machine learning. It was invented for convolutional neural networks. But there are, of course, many such embedded matrix-matrix multiplies, for example, in dense Gauss elimination. And so if we structure our computations accordingly, we can exploit these far more generally. And if we do so in lower precision, we generally get more than 2x improvement for having the precision, largely because the data for the same number of words lives higher on the memory hierarchy. So it's not just cheaper flops, but it's cheaper data motion. Let's look at the power efficiencies of the 181 entries of the June 2021 Top 500 list, the most recent, that are kind enough to report their power efficiencies. I've histogrammed them here from 1 to 181, and all but 3 of the best are accelerated, typically today with GPUs. The most efficient is nearly 31 gigaflops per second per watt. The least efficient is more than 2 orders of magnitude less so. And the median is about 3.5 gigaflops per watt among the world's top systems today. So you see there's a lot of potential to become more power efficient if we can use these more complicated SIMT kinds of operations. Well, we have to be conscious about reducing our favorite operation, the global reduction, whether it's an inner product or a max operation for CFL or whatever. This is the red curve is repeated from John McAlpin's chart for a one-core system. If we look at an all-core system and we stall on an MPI for an MPI receive, for example, that is going up by 40% per year among top commodity chips. And let's not hide from ourselves that we are very dependent on these bulk synchronous operations. Most petascale, most simulations today rely on data decomposition and message passing. And the message passing is typically synchronized. We have a bulk synchronous model, sometimes it's called single program multiple data, or communicating sequential processes. We do a volume of computation for a surface amount of communication, and we tend to do all that communication at the same time, which congests the network rather than spreading it out in a more time-shared way. Well, this bulk synchronous way of programming has done a lot of good for computational science and engineering. If you track the Gordon Bell Prize for 20 years, you see a factor of 1 million improvement in flops delivered to applications, and a factor of many hundreds of thousands of improvement in the cost per installed gigaflops. But this entire edifice of bulk synchronous code, which pervades computational science from climate to chemistry to combustion and so forth, has to be replaced because we can't afford to globally synchronize anymore. Or we have to synchronize as little as we can in order to not be slowed by some random fault or one of let's say 1 million threads that is slower than all the other ones. And let me point out that we already have 10 million threads on Taihu Lite, the number 4 system in the world, and to get an exascale at 1 gigahertz means we'll need the equivalent of about 1 billion such threads. So we need to also reduce communication in number and volume. And to give an idea of why that is so essential, let me point to a 4-year-old paper from friends at Livermore, where they looked at 3 core solver kernels, a geometric multigrid code from Berkeley, an algebraic multigrid code from Livermore, and a spectral element code from Argonne, all of which run on the DOE's top systems. And they hypothesized using simulations, what would happen if we multiplied our bandwidth of the network by 1, 2, 4, and 8. And only one of those 3 codes could take much advantage of the extra bandwidths. The other ones were choked in their algorithmic structure from even taking advantage of a very expensive form of hardware improvement. So why do we need to exploit heterogeneity in processing memory and networking elements? Well, that's where the top 500 systems are providing their flops now. This chart is actually a year old. This was from Eric Strohmeyer's 2020 chart. It's about the same. There's now about 180 systems in the top 500 that are accelerated. The majority of them nowadays by the NVIDIA systems. If you look just at the top 5 systems over the past decade, and this is a paper from friends at Oak Ridge, you see that all of the top 5 have been heterogeneous in diamonds for the last few years. And the gigaflops per watt is up in the 15 domain for these top 5. Remember, the peak was around 30. So if you want to fit your problem onto the world's largest systems, you're going to be dealing with these heterogeneous processors. And maybe in the future, some of those onboard cores will not just be thin GPUs. Maybe there'll be a quantum accelerator, a neuromorphic accelerator, an MLDL tensor core accelerator, all of these accessible on the same chip and ready to use. Well, your cell phone knows how to use these things. It has about 40 different specialized processors to do your imaging, your voice recognition, your various special operations that make that system so energy efficient. You don't want to have one processor to handle all of those very disparate kinds of operations. And that same philosophy is coming to scientific computing. So much for architectural imperatives. What are some established means of coping? Exploiting extra memory to reduce communication volume. And I have to be very quick here to get through my list. But several years ago, Demel's group at Berkeley showed that most of the linear algebra codes in Scala-Pak fail to achieve their communication theoretical lower bound, which is given by the number of arithmetic operations divided by the square root of the size of fast memory. Nowadays, the Slate package is being redesigned to use any extra memory per node, depending on, of course, the problem size, and put that into reducing the communication. Here are two examples in which the green is computation and the red is communication and the blue is idle. And these are some early runs by Demel's group showing how the communication can be reduced to a very small fraction of the total with overall runtime improvements ranging from 2.5 to 10 for different problem sizes. If you have smaller problem sizes, there's more of that memory available to make up for the communication. Perform extra local flops to require fewer global operations. And I would like to call attention here to the excellent work of our friends from Belgium, Giesels and Van Rooze from many years ago, showing how pipelined conjugate gradients, where instead of doing an inner product after every matvec to conjugate the vector and perform the minimization of CG, you store up many steps before you do the inner products. That means you're going to do more arithmetic when you finally get around to doing the inner products, but you actually can make huge improvements in solving the system. You do more flops, you use more memory at an intermediate stage, but you do less synchronization, and the net result is nice speed ups. What about high order discretizations? Well, this really goes back to a 1972 paper by Kreis and Oliger, who argued that second order discretizations are very wasteful of memory compared to fourth order, where you can get the same accuracy for many fewer degrees of freedom. That was less relevant at the time than it is now, where we have to live higher in the memory hierarchy. And this is an example from my own group of a few years ago on a Cray XC40 using a spectral element method, where by going from 8th order to 16th order, you can cut the overall runtime by a factor of 8. You have many fewer elements. The elements are of higher order. You can exploit the high density of flops per byte. And for this set of sort of fundamental turbulence calculations in a pipe, it was the way to go. The same error in a key functional, but the savings in execution time nearly an order of magnitude. And you can see here how that plays out over the element size from 4th order to 32nd order in terms of 4 different matrix libraries. And the curves on top are the gigabytes per second realized in memory bandwidth. So you can still get a high percentage of the peak of memory bandwidth while operating at a higher gigaflops ratio. What about adapting floating point precision to the accuracy requirements? Well, I'd like to call attention here to some excellent work in climate modeling by our colleagues in the UK at the European Center there, who have been experimenting with using lower precision floating point words, even down to half precision, not just single, but down to half, in conventional global climate and regional climate codes. And you can see here a comparison on the top and the bottom of the double precision and the single precision, which delivered these forecasts at about 40% less cost. And one could argue at qualitatively very similar results. you can see some disparate results in the contours in isolated portions of highly sensitive parts of the computation. But the Legendre transform, the Fourier transform, the nonlinear advection, and the linear operations were all executed at reduced precision. And the same group has been addressing overcoming hardware errors with algorithmic fixes. So the top row here is a fully deterministic calculation with hardware error correction. The bottom row has perturbed the high frequency modes with stochastic bit flips. And you can see the forecasts are essentially unaffected by the introduction of all of these errors in the high frequency mode. Now, this is obviously a simulated run, but the point is that we could now invite computer vendors to supply heterogeneous hardware with some highly reliable nodes and some lesser reliable nodes, which are much more energy efficient. And if we allocate our computation and our data storage to the high and the low reliability processors and memory respectively, then we can extract the same scientific information at much less cost. So these are established practices. What about some that are in development as I head towards my final 10 minutes here? Well, here's an example of a task graph for doing a symmetric eigensolver on a multi-core architecture, whereas instead of a single block of the matrix, it's divided up into 16 blocks. Ordinarily, you would go to much finer granularity. But what you see here is the traditional algorithm on the left-hand side, where you would do a Cholesky factorization of the B matrix. You would apply the inverse factors to the right-hand side to get a conventional eigenproblem, and then you do tridiagonal reduction and finally QR iteration. And if you do those 6 steps sequentially, you have to stack up these charts here where time goes from top to bottom and width represents the concurrency, the number of operations that can be done at the same time. And on the previous slide, I showed what you get if you break up those subroutine boundaries and go directly to a task graph. You compress the vertical height, which represents time. You widen the available concurrency, and the results in runtime are shown here for a traditional sort of single block plasma. The plasma is the multi-block version, the new version. LAPAC is the old version, and you can see a 21x speed up on the same hardware by just improving that aspect of the organization of an identical computation in identical precision. What about coding to specialized backends? Well, this is the way the internet works. You know very well that you have many applications like checking your bank balance, ordering shoes, or doing climate modeling on the cloud. And all those different kinds of operations are mediated through a common internet protocol. And to you just look at your browser. Well, wouldn't it be nice if we could organize scientific software that way so that we could express things in MATLAB-like notation, solve my eigenproblem, do my least squares fit at the user level, and have that farmed out to whatever architecture is best or most available at the bottom level. Well, of course, to provide that inner layer of algorithmic infrastructure requires a small number of ninja programmers who know about non-temporal stores, bypassing cache, coalesced memory accesses, double buffering, etc., to produce these advances. The code is complex. The code is architecture specific at the bottom, but it's ultimately a pathway towards exascale exploitation for general users. We need to exploit data sparsity. This is actually my favorite subject of them all at the moment, to meet the curse of dimensionality with the blessing of low rank. I refer you to one of our recent review papers in the Philosophical Transactions of the Royal Society. And by the way, Nagaya has these slides and is welcome to make them available as soon as the workshop is underway. But there are now many ways of representing a fully dense matrix in a hierarchical format in which off-diagonal blocks can usually be represented if they're coming from something physics, something with a potential type solve, something gravitational or electrostatic or covariant like, any of these many problems that come up in statistics and computational physics. Typically, and it's the basis of the multipole method, off-diagonal blocks are distant from each other. They represent interactions that are distant, and they can be hierarchicalized in various ways in order to permit various desired degrees of off-diagonal ranks for a given accuracy. And I don't have time to go into the subtleties of this, but here are the fruits from doing these kind of analyses. Whereas a straight Gauss or Cholesky decomposition would cost you n cubed, the tile low rank is n squared times the block rank to the half power, and the full hierarchically low rank after, for example, Huckbush is only order n log squared of n times the local rank squared. The local rank may be 10 for a block size of 1,000. So you can see how well these algorithms may work in practice. Perhaps more importantly than the reduction in flops is the reduction in storage to represent a problem to a desired accuracy, eliminating a full power of n. So if you're got a million by million covariance matrix, instead of taking 1 trillion double precision floats, which is 8 terabytes, you could probably fit it into, let's say 10, megabytes. And that's, to acceptable accuracy to a statistician. We want to process on the fly rather than storing those large dense matrices. We want to be able to accomplish these hierarchical matrix by hierarchical matrix multiplications in the order of seconds rather than the order of hours when manipulating dense matrices that are on terabyte scale deep down in the memory hierarchy. And this shows what can be done on a single GPU for problem sizes ranging up to 250,000 dense, but compressed in acceptable compression for different tolerances. And you can see this green line is order n log n, and these are 2 different implementations with 2 different accuracies, and they do follow that n log n curve. If you can do fast H matrix multiplication, you can resurrect a beautiful algorithm that was never really practical, the Newton-Schultz matrix inversion method, which depends on map multiplications. Finally, co-design algorithms with the hardware. This is a recent paper with a colleague in Norway, Mikael Mortensen, exploiting features of advanced MPI. By the way, MPI 4 just came out a few weeks ago. But even before that, with MPI 3, there was an operation called MPI all-to-all W, which is actually an operation that is able to do transposes while the data is being mailed between 2 different processors. So MPI has an instruction that can offload the transpose of the FFT to the network. Now, unfortunately, most vendors have not yet implemented that instruction in hardware. They implement it in the standard CPU or GPU itself. So by migrating our FFT code to this new feature of MPI, we do not actually see much savings, but we are now inviting the architects to go ahead and put this transpose into the hardware where it belongs rather than clogging up the CPU or the GPU in doing FFTs. So this is true co-design in which a facility that an algorithmicist identifies can be fed back to the architects instead of the other way around, which is the way we've been suffering mostly for the last 30 years, in which the architect makes some design motivated purely by the Linpack benchmark or by machine learning. And then we in computational science have to figure out how to use that commodity hardware. And so I think we're moving to a place where a better conversation is beginning to occur between the top and the bottom levels of the scientific tool chain And to that end, I commend the pursuit of your own research in your new institute. And I think I have a minute or two for questions. And so I say thank you very much, shukran, and I look forward to our future interactions.
Yeah, so thank you so much, Professor David, for an enlightening and excellent presentation on the scalable solvers for CSE. So now the talk is open for the questions. So if you have any questions, you can write in the chat box, or you can ask, unmute and ask.
And I remind that my slides are available because I know that I went unfairly fast through many things, but my desire was to communicate a range of topics for mutual investigation.
Yeah, so thank you so much for allowing to use the slides. So I'm sure I will make it available in the website. So I don't see any questions on the chat box.
So may I ask a question?
My privilege, Peter, to hear from you.
Hello. Hi, David. Of course, excellent talk. Thank you for this excellent overview. So you talked about heterogeneity, and of course, we have it, but I'm still not a fan of it. I always out myself with that. Because I'm always thinking now we have these GPUs and the CPUs on these nodes, but I think not many people are actually using both. So they are either using one or the other, and I think it makes sense. But then always one half of the hardware is not used. And for example, there were announcements some years ago to put some small CPUs in the GPUs so that they could be standalone, but somehow this was never realized. I'm not exactly sure why, but so to me, this is still strange that we have two things and we only use one.
It's true. But is it strange that in our cell phone, we have a separate, movie player from a separate sound, when you dictate and it turns your speech into text? I mean, the goal, I accept your point readily, by the way. And it's true that on the systems like the Summit machine, you have some people using only the GPUs and some people using only the CPUs. Fortunately the CPUs are such a tiny percentage of the whole that if you're mainly using the GPUs, you're getting the most of the system. But I would argue that the sort of premium that we should put on evaluating efficient use of these systems is getting the computation done in the quickest amount of time and releasing this energy consumer to somebody else. And if that means that at one point, the limiting reagent is the bandwidth, at another point, the limiting reagent is the CPU and so forth, then at least if we are performance modeling that, we can move our software into the best engineered niche for a given system. It's true that we may not be using many parts of the system, but then again, for today's bulk synchronous computations, we don't use the network except for 1% of the time. We compute, and then everybody crams onto the network all at once with some global message, using it extremely inefficiently, but we still pay half the cost of the machine for the network because we need it to make the other part work. So your point is extremely correct in terms of the inefficient use. And I know that your group makes very efficient use of multi-core in terms of stencil evaluation and and organizing matrix computations. But to the extent that you're not using something, it's part of the overall optimized configuration, I would argue. So I've stopped losing sleep over percentage of peak, as long as maybe we're getting something done quicker with less energy. One answer.
Yeah, thanks.
Yeah, so it seems there is a question from the chat box from Shraddha. So could you comment on the double precision computation on GPU for the H matrix computation, comparing with the computation on CPU?
Yes, I could. the H2 Opus library, H2 OPUS, which my student Waji Bukaram wrote, which was used to do that HH multiplication, is both GPU and CPU compatible. It looks the same at the top level. And I would say that the GPU is on the order of 10 to 20 times faster for that. It's just a question of the way you can batch things efficiently. That's not a universal number to be quoted for all matrix sizes and all operations, but it's sort of typical that the same double precision, when it fits in GPU memory, is on the order of magnitude faster. Now the catch there is, of course, that GPU memory is not very large, and that's why we're so interested in the hierarchical representation, so that an effectively larger problem in the mathematical sense can fit on a GPU in the memory sense. And of course, there's always an accuracy compromise there. You set your tolerance, 10 to the minus 6, 10 to the minus 8, 10 to the minus 12, whatever you want. Your ranks will be higher if your accuracy requirements are stricter, and therefore your problem sizes that fit on a GPU will be smaller because you'll need to put more of the dense matrix. But you find that sweet spot based on your application and your hardware. And GPUs are getting bigger and more people are making them now. And it's almost, the name GPU almost is irrelevant now. I mean, it's not a graphical processor, it's a universal processor with these characteristics of batched operations.
Okay, thank you so much. So if you have any questions, please, you can post in the chat box. So to keep a program on time, probably we will move to the next speaker. Thank you so much. Thank you, Professor David, for excellent talk.
Thank you very much.
So see you again.
Yeah.
So Professor Peter, can you share your slides?
Shall I share my screen?
Yeah.
Can you see it?
Yeah.
Can you see?
Yes, I can see. Okay, so it is my great pleasure to introduce our next speaker, Professor Peter Bastian from University of Heidelberg, Germany. He is very well known in the scientific computing community, and here I will give a short bio sketch of Professor Peter Bastian. So Peter Bastian studied computer science at Erlangen, Nuremberg University, Germany, and obtained a doctoral degree in mathematics from University of Heidelberg in 1994. After his habilitation at Kiel University in 1999, he obtained professorships at Heidelberg University and University of Stuttgart. Since 2008, he has been a professor and head of parallel computing group at the Interdisciplinary Center for Scientific Computing, Heidelberg University. Also, he is a chairman of the Heidelberg Graduate School of Mathematical and Computational Methods for the Sciences. This is one of the largest graduate college, that's what I know, in Germany. And his scientific interests include the numerical solution of PDEs, applications in fluid flow, high performance computing, software design, and computational neuroscience. Most importantly, he is one of the co-developers of Dune package, which is a general partial differential equation solver software package, which is available freely. Today, he is going to talk about trends in high performance finite element simulations. So please put your hands together for a warm welcome to Professor Peter Bastian. Now I will hand over to Professor Peter Bastian.
Thank you, Nagaya, for the kind introduction and also for inviting me here to speak at this workshop here for the inauguration of your new computer and institute. Of course, it's quite hard to speak after David Keyes. He gave such a nice overview. So a little bit I anticipated that, so I will try to keep it short to give you some background on HPC, which will not give much new above that what David has already been given. And then I will concentrate on two approaches. In particular, the matrix-free finite element, high-order finite element method that was mentioned as well. Yeah, so I will give you some detail on that. And I will also concentrate on robust iterative solver on the other hand. So these are two kind of complementary things, in particular spectral domain decomposition methods. So let's dive in a bit. Yeah. So some background on HPC. We all thrived on Moore's law in the last decade. So basically all my life, Moore's law has been going on. So here you see the number of transistors you can put on a chip or on a CPU chip from 1970 to 2020. And actually in this diagram, you don't see any sign of it slowing down. So these are 26 doublings at 50 years. So it's almost exactly the 2 years period. And you would not notice that it's actually supposed to end within the next few years or within the next decade. This will, of course, not happen immediately. So it will happen gradually, and it already happens. So one figure I found very interesting is this one here. So when you look at this diagram, you see the number of transistors you can buy per dollar. So that's actually the economic part of Moore's law, because he said that the number of transistors you can put most economically on a chip would double every year, and then it was every 2 years. But here you see that the number of transistors you can buy per dollar, it actually reached a plateau around 2010, and now it's actually decreasing again. Yeah? So now we are in the technological part of Moore's law, but not in the economic part anymore. And actually that's also supposed to end due to physical reasons. As has been pointed out before, trouble started even earlier, and that was when Dennard scaling ended. Yeah. So before around 2005, so that's this line here in this right diagram, the clock rate was steadily increasing of the chips that have been built, and also the power consumption has been steadily increasing, and this could not be sustained anymore. So since then, the clock rates are stagnating or even have been going down, and the power needs to remain constant. But still, we have this increase in the number of transistors. And here's a one-slide summary of some of the, or most of the things that have been said already. So what are the challenges for our scientific computing algorithms that basically come from the end of Dennard scaling? It's that we have to live with a massive amount of parallelism in our algorithms and in the hardware on different levels. So in particular, there's instruction level, which shows itself by the use of pipelining, multiple instruction issue, and in particular, the SIMD vector instructions. So as has been said, without using SIMD vector instructions, you cannot get anywhere near the peak performance of today's machines. We have lots of parallelism on the node level by executing many parallel threads communicating via shared memory. And for large systems on the system level, where we replicate nodes which are communicating by passing messages over a network. Locality has been mentioned already. So for decades, memory bandwidth has been growing slower than the instruction throughput. So that's not a consequence of Dennard scaling. It has been around since the advent of the RISC processor all the time, basically, when we had integrated processors, and latency grew even slower. And this memory gap has been filled by the cache hierarchy or fast local memories in GPUs. Then we discussed already about heterogeneity. So these accelerators, they basically trade in the transistors used for control logic and for caches in CPUs to have more of simpler cores. and thus are more energy efficient. And basically these, from a programmer's point of view, accelerators are executing SIMD instructions all the time. So you don't have any scalar instructions anymore. It's basically all SIMD instructions, and they are even wider than on CPUs. And so your algorithm needs a lot of structure and predictability to exploit this hardware. And accelerators are typically equipped with faster memory, so-called high bandwidth memory. And fortunately, there's an exception now with the new #1 system, Fugaku, which in my thinking is a good sign because it has put some of the nice things we have from accelerators to CPUs, yeah? In particular, the high memory bandwidth. Also, with respect to resilience, that's a subject we already discussed at the petascale. And after all, it was not necessary anymore. It was not necessary to have user-level fault tolerance on the petascale machines. And I'm very interested to see whether we will really need it on the exascale systems. Something that I think is very important from an algorithmic point of view is the roofline analysis. And I think it cannot be overestimated its importance. And so therefore I wanted to present it shortly. So the roofline analysis, it basically divides the world of algorithm into two parts, namely the world of memory-bound algorithms and the compute-bound algorithms. And it's the first thing that we should look at in our programs. It's defined as follows. So you look at the so-called machine intensity. So that's the peak performance of your machine divided by the memory bandwidth. So peak performance is flops per second. Memory bandwidth is bytes per second. So the seconds cancel out and you get something which has the units of flops per byte, and it indicates the number of floating point operations you have to execute per byte loaded from memory when you operate at machine intensity. And this can be used now to predict the performance of any kind of algorithm by computing this algorithm's intensity. So either theoretically or practically. So theoretically would mean that you look at your algorithm and implementation and count the number of floating point operations it executes at unit time. And then you count how much memory it loads for executing these flops in unit time. And that's the algorithmic intensity I. And then this formula predicts you the performance of your algorithm at a certain intensity. And it turns out you are either, your performance is limited by the memory bandwidth when your intensity is lower than the machine intensity, or you are operating possibly, or you could theoretically operate at peak performance when your intensity is larger than the machine intensity. Now, these are the numbers here for my laptop. Yeah, so it has a memory bandwidth of 37 gigabytes per second. It can perform up to 180 gigaflops per second. So it has an intensity of around 5 flops per byte. So what are typical intensities of algorithms? For example, when you look at a double precision scalar product, you would have an intensity of 1/8. For a double precision matrix vector product, you are at 1/4. There are better algorithms, for example, matrix multiplication using tiling. Then it depends on your tile or block size. So with a block size of 64, you could achieve in double precision an intensity of 8. So with that, I could come into the compute bound regime. But many algorithms that we use in scientific computing, they are often memory bound. In practice, it's a little bit more complicated because you have different memory bandwidth depending on the type of memory that you are using. Yeah? So when you are using, when your data fits completely in the L1 cache, then you would have this line here. And you have different peak performances according to what kind of instructions you are using, scalar or SIMD instructions, or whether you are using one or all cores of a system. Yeah? And this gives you different machine intensities correspondingly in this diagram. So, but what you want to do when you develop an algorithm, basically in the roofline diagram, you want to go right, increase your compute intensity, and then you want to go up to fully exploit the hardware that you have. So that's the general goal when you develop an algorithm for a high performance system. And in increasing the performance, we can then also separate into achieving high node level performance, which is often today the most difficult part, because there you have to efficiently use the SIMD vector instructions. And with increasing core counts, we should also use shared memory, at least in between uniform memory access domains. And on the system level performance, we need lots of coarse-grained parallelism with a high computation to communication ratio. So that was the communication avoiding and communication minimization part that David already mentions through asynchronous and algorithms that basically hide the communication behind the computation. So let me now come to the PDEs and the finite element method to somehow expose these things. So problem-wise, we are interested mostly in fluid flow problems. The most simple example would be groundwater flow, which is governed by an elliptic partial differential equation so a second order elliptic equation here for the unknown function u, which describes pressure or hydraulic head. It also uses a parameter k with this, which describes the permeability of the subsurface. And of course, some Dirichlet or Neumann boundary conditions and sources and sinks. An important problem in practice is that the permeability parameter in groundwater flow can vary over orders of magnitude. And you often have anisotropic domains or then consequently anisotropic grids, and sometimes also anisotropic permeability tensors. So the K is a D by D matrix, which adds to the difficulty of that problem. For the finite element discretization, we use high order methods, and in particular, for these kinds of problem, a suitable method is the weighted symmetric interior penalty discontinuous Galerkin method, which can very effectively handle these highly varying and anisotropic permeability tensors. So it leads, after some manipulation of the strong form here, to a discrete weak form of this equation where the bilinear form A is a symmetric and positive definite bilinear form, and L is our right-hand side linear form. So this bilinear form involves computing some element-wise integral and some phase-wise integrals. So the details are not too important here. You should only remember that it has element integrals and phase integrals on a given mesh to carry out. And after inserting a basis representation, you have to solve a linear system AX equals B with a sparse and symmetric positive definite matrix A in that case. This can be made more complicated, for example, by augmenting the flow equation we had before by a transport equation for some dissolved substance given by the concentration C. And now, for example, the density or the viscosity of the fluid could depend on that concentration, which gives rise to some instabilities. So that's, for example, the miscible displacement problem giving rise to viscous fingering, an important problem in the oil industry. We also have worked on the incompressible Navier-Stokes equations, which can be discretized with a similar discretization scheme. And in particular, when you use an operator splitting method, you essentially have to solve a Poisson equation inside, so which is, again, our elliptic equation. And also for the momentum equation, you could use a discontinuous Galerkin discretization, which has good properties for transport dominated and convection dominated problems. So here are some examples here, especially for the robust solvers I will mention later, they would also be very effective for linear elasticity type problems, which you see here. So here we have been modeling carbon fiber composites, which are also characterized by a very heterogeneous and anisotropic stiffness tensor C here. And again, you would result into a linear system AX equals B in the end. So in the finite element method, for example, for our elliptic PDE, as we have seen, we have to solve these large and sparse linear systems. And typically we use iterative solvers to solve these systems where, and here I've put the simplest type of iteration here, a linear iterative iteration, where you have to compute the defect here, which basically involves a matrix vector product, and then you have to apply a preconditioner B. And there are basically two kinds of approaches that you can take. So one approach are matrix-based methods. So they would assemble the matrix A in some sparse matrix format, like LPAC or compressed row storage. So depending on the kind of architecture, there are different choices for these formats. But in the end, all these methods would always be memory bound in terms of our roofline analysis, because the arithmetic intensity of a matrix vector product is below 1/4. So it would be 1/4 for a dense matrix vector product, and it's even smaller for a sparse matrix vector product, because you have to load also the column indices. But the advantage of these matrix-based methods is that you have highly effective preconditioners B available that would lead to a very small number of iterations in this iterative scheme. Yeah? So that's the advantage here. So for example, algebraic multigrid method or domain decomposition methods, where I will concentrate on later. On the other hand, there stand matrix-free finite element methods. So these can be used to get into the compute bound regime. So we can increase the arithmetic intensity. And within the matrix-free methods, we can discern switch between low order methods and high order methods. So to get a matrix-free low order method, you have to exploit structure. For example, that you have regular grids or that you have constant coefficients like in a real Poisson problem. And you can now use SIMD vectorization over several elements. But put simply, it's relatively hard, at least for finite element methods, to recompute the matrix entries faster than loading them from memory. It's somewhat simpler for finite difference methods, stencil-based methods, which are less complicated. So there you have less operations per grid point, and then these methods are viable, but for finite element methods, it's pretty expensive. It's completely different when you go to high order finite element schemes, because there you can exploit so-called tensor product structure. So when you go to high order finite element schemes, the complexity of computing a matrix vector product, so applying your finite element matrix to a vector, depends on the number of elements, which is this h to the minus d part here. and it depends on the polynomial degree, which is the work per element that you have to do. And it's something like p to the power 2d, where d is the space dimension. So in 3D, the work would increase like polynomial degree to the power 6. And this complexity can be reduced considerably by exploiting tensor product structure to p to the power d plus 1. Then you can even vectorize within one element because you have so much work to do per element. So the challenges here are how you can do a high performance matrix-free implementation of the discontinuous Galerkin method. So that I will show you in the next few slides. And then how you can get robust matrix-free or matrix-based iterative schemes. So let's look at the matrix-free finite element method and exploiting this tensor product structure. So in the finite element method, you have to express your unknown function u in terms of a linear combination of basis function. So we have a number of basis functions, phi j, and each of these basis functions, phi j, we assume now we can write in a special form like a product of one-dimensional basis functions. So that's particularly easy to do on cube-like elements. So that's the natural thing to do there, to write the finite element function on each element as a product of one-dimensional functions. And now when you exploit that, so you write your finite element function, you want to evaluate it at a point, psi I here, so that's a quadrature point. You insert your representation as a sum over the basis functions, and then you insert the representation of your basis function here as a product of one-dimensional functions. And you not only have to do this for one quadrature point, but you have to do that for many quadrature points at once. Yeah? So there are parallel evaluations of that for many quadrature points. And so you can collect all these evaluations of the one-dimensional basis functions at the one-dimensional quadrature points in little matrices. Yeah? So when you have 4 quadrature points and 4 basis functions, you would have here a 4x4 matrix here. And you organize this in these little matrices, and you can then write the evaluation of the finite element function at all the quadrature points in terms of a matrix vector product. Yeah? And this matrix A here has a special form. It's namely a Kronecker product of these very small matrices. So the matrix A may be large, it may be several hundred times several hundred dense matrix. We are now on one element, but it's actually made up of very little information, namely these D small matrices, which consist of the one-dimensional basis functions at the one-dimensional quadrature points, which are, for example, 4x4, for example. And interestingly enough, the same structure can be obtained for evaluating the bilinear form. So that's the much more complicated part. I didn't show it here because it's too technical, but essentially evaluating the bilinear form for all the different test functions comes down to exactly the same thing here. And so the question is now how you could evaluate such a matrix vector product with such a Kronecker matrix here efficiently. And that's sum factorization. And it's actually very simple. It's extraction of common factors. Yeah? So we have a default sum over this default product of these entries of these little matrices times our coefficient vector. And now you see, when we look at this default sum, that these numbers down here, they all do not depend on the first index J1. So only here we have the J1 and here we have the J1. So we can put out the product of these numbers outside of the first sum. And when we do this, we have here the sum, which we can evaluate. And here now we have one sum less. And we again have a product of these entries of these little matrices. And we can play the same trick again. So here we have J2, here we have J2, here we have a J2, but here we don't have J2, so we can put that out. And you can do this D times, and you have computed your product. So the nice thing is that this reduces complexity now, and you can write down a matrix-free finite element algorithm or operator application in the following way. So you loop over all your mesh elements. Then you gather all the coefficients from your big coefficient vector for this element. Then you compute the finite element function and also its gradient in a second order problem at the quadrature points. This can be done by some factorization with this complexity. Then you have to evaluate some PDE coefficients and geometry factors coming in for the integration. But this is work that's constant per quadrature point. So it's only p to the power d work. Then you have to compute your finite element integrals. This can be again done with some factorization. It's again p to the power d plus 1 work. And then you have to scatter the contributions to the result vector, so which is again a memory operation. So, and these are done completely local once you have loaded the data in your local memory. And you have this significant reduction from p to the power 2d to p to the power d plus 1. And there's even more, another important point. When you do the sum factorization, you have to do these intermediate sums here. And it turns out you can write these intermediate sums here as matrix-matrix products. So it's not only that we are reducing the complexity considerably, but we also write our algorithm, or the most costliest part of the algorithm, the step 2 and 4, in terms of matrix-matrix products, where you can achieve a high performance. Unfortunately, these matrix-matrix products consist only of very relatively small matrices. So it's something like a 4x4 times a 4 times 16 matrix, but you have to execute many of them. So it's batched little matrix-matrix products. That's kind of a challenge to do this effectively, but it can be done. So to give you some impression, here are some results on 2 different kinds of processors: a older Haswell processor having AVX2 and having a with 2 times 16 cores that results in a little bit more than a teraflop peak performance. So 36 gigaflops is the performance per core, and using 32 cores we get this performance. And we have a Skylake node having 40 cores, having 70 gigaflops per core, and in total it's something like 2.8 teraflops. And here you see a comparison of this matrix-free versus a matrix-based operator application. So here we used a matrix assembled into PETSI, and then the matrix vector product done in PETSI. So that's this part of the table here. We increase the polynomial degree here from 1 up to 9. And you see we are performing always around 25 to 30 gigaflops, which translates into a memory bandwidth of about 100 gigabytes per second. Yeah? So our algorithm is clearly memory bandwidth limited at that point. So that's very far away from the peak performance, and that's basically the memory bandwidth you see. Consequently, when you look at the number of degrees of freedom we can process per second, then this goes down because we have more work per degree of freedom in a high order method. The number of degrees of freedom we can process per second goes down by 3 orders of magnitude here. When you look at the matrix-free part, you see our performance is already better at polynomial degree 1, and it goes up to close to 500 gigaflops. So that's something like 40 to 50% of peak performance as we increase the polynomial degree. And when you look at number of degrees of freedom processed per second, you see it roughly stays constant. Yeah? So we can compute the same number of degrees of freedom as we increase the polynomial degree. So we pay essentially nothing for increasing the polynomial degree and get a much more accurate solution. When we look at polynomial degree 9, so you see that we can process more than 3 orders of magnitude more degrees of freedom per second. And this performance increase comes from 2 things. So it's about a factor of 100 that's done by the reduction in flops by the sum factorization. And you see it's a factor of 20 we get by increasing the performance from memory bound to compute bound and using SIMD vector instructions. So it's really a nice coincidence here that we can at the same time do less flops and have a higher compute intensity. That's, say, a very rare coincidence for this kind of algorithm, but it's very useful in the finite element method. So here are more results. Here on the Skylake machine, we can get to something like 900 gigaflops. And here's again the number of degrees of freedom processed per second is again roughly constant over the polynomial degree. And so now we can do operator application, so matrix vector product. The question is now, how can we solve a linear system? So we need a preconditioner. And here we use subspace correction methods. So subspace correction methods work as follows. You have to solve such a discrete variational problem. Then you split your finite element space into a number of subspaces. And the subspaces that we choose here, there will be a subspace VH0, which consists of a low order finite element space, say the piecewise constant or the piecewise linear conforming finite elements. So they are both a subspace of the discontinuous Galerkin finite element space. So they live on the whole domain, but they are low order. And then we have an additional small subspaces related to each element, which are high order. So here we use our high order DG functions, but only element by element. And then we can do a hybrid subspace iteration, which means we are solving in a first half step, we solve matrix free in parallel on each of the elements. So this is basically a Bloch-Jacobi preconditioner on the high order part, which we can do matrix free or partially matrix free, as you will see in the next table. And then we solve in this low order global subspace. And this we do approximately by applying 1 AMG V cycle. And here you see some results. So this is Poisson equation or a variable coefficient problem for different polynomial degrees, rather low polynomial degree. So this is the matrix based method, matrix explicit. And here we have the matrix free method where we do inexact local solves with rather low accuracy. And you see we get some improvement here. So we, in all cases, we are faster than the matrix based method. And the fastest variant for these polynomial degrees is actually to be partially matrix free, where we do the operator application, so the A times X matrix free, but we do the local solves in the Bloch-Jacobi matrix based using a factorization and back substitution. But this becomes different when you go to higher polynomial degrees, then the matrix-free method typically beats also the partially matrix-free method. Let me now come to a complementary subject. Yeah, so now we focused on performance. in the matrix-free part, now we focus on robustness. Sometimes the linear systems are very difficult to solve, and the matrix-free preconditioner I presented above, it would be H robust, so robust in the number of elements, but it's only fairly coefficient robust. When you have highly heterogeneous coefficients, say in linear elasticity, then the number of iterations would actually increase. So this is now a method that is provably robust for really hard problems, for any coefficient distribution, for example, for the permeability or the stiffness tensor. Of course, that's a very well-investigated subject, robustness for hard permeability distributions. For example, there are algebraic multigrid methods. They have a limited amount of theory, so I would say the theory is not as rigorous as for the domain decomposition method I will present. But I would like to point out spectral AMGE, because that's kind of the basic idea also behind the spectral DD methods, is to solve local eigenproblems to construct the coarse approximation. And then the other class of scalable preconditioners are overlapping domain or domain decomposition methods, which come as overlapping or non-overlapping methods. And they typically employ two levels in order to get independent of the number of subdomains. In their basic variants, they are usually not coefficient variant, but coefficient robust, but rather only H and P robust. But now there are so-called spectral domain decomposition methods, which again solve local eigenproblems in the subdomains to achieve coefficient robustness. And our method in particular is based on the so-called GENIO method, which stands for Generalized Eigenproblems in the Overlaps, in this paper by Spillan and Frederick Nataf and Rob Scheichel and others. And so we extended this method now to a multi-level spectral domain decomposition methods, because two-level domain decomposition methods are not scalable to current machines having up to, say, 10 to the power 7 cores. How much time do I have, Nagaya? I have to be careful.
Yeah, maybe 10 minutes.
10 minutes. Okay, that's fine.
Yeah, fine.
Okay, so two-level methods, they would not scale to current machines. So when you look at spectral domain decomposition or methods, then the dimension of the core space that you would use would be proportional to the number of subdomains. So that corresponds to the number of computers that you have. And in particular for spectral domain decomposition methods, the dimension of the core space would be something like 10 or 20 times P, which is way above what you can solve efficiently even with a parallel direct solver. So this limits the scaling of two-level domain decomposition methods, in particular spectral two-level domain decomposition, to around 10 to the power 4 cores. So we are 3 orders of magnitudes more that we need today. So we need an extension to multiple levels, to more than 2 levels. But typically 3 or 4 levels would be sufficient. To contrast that to traditional algebraic or geometric multigrid methods. So in multigrid methods, you would start on the finest level with your individual degrees of freedom, which would be, say, 1,000,000 times P. Yeah? So in every processor, you have 1,000,000 degrees of freedom. And you would have a rather small coarsening factor, something like 4 or 8 in 3 dimensions. So you would need correspondingly many coarsenings, many levels, until you reach a system that you can solve with a direct solver. So in these multi-level domain decomposition methods, you start on the finest level with the number of subdomains. And you use a very aggressive coarsening factor, something like coarsening by a factor of 100 or more for each level. So you only need 3 or 4 levels to be able to scale to 10 to the power 7 cores. Again, the way to go is a subspace correction method. So you want to solve your discrete variational problem. And again, you subdivide your finite element space into a number of subspaces, n here in this case. Whenever you have such a structure into subspaces, you can do parallel subspace iteration by locally solving in your subspaces and combining all these solutions in these subspaces. So here it's written as a standalone iteration. So there you need some damping factor, but typically that's used as a preconditioner in conjugate gradient or some other Krylov method, and then you don't need the scaling factor. And other variants are possible. You can also include multiplicative parts. So in multi-level spectral DD, we devise these subspaces here in kind of a 2-step procedure. So first we have a multi-level hierarchy of finite element spaces. So that's kind of the vertical splitting. So we start with our finite element space and could produce coarser spaces of smaller dimension until we reach some coarser space where we employ a direct solvent. And each of these levels, except the coarsest one, is now split into subspaces related to subdomains. So that's some kind of vertical decomposition. And now let me explain how we construct this vertical and horizontal splittings. So it's based on a corresponding multi-level domain decomposition. So here on the left, you see, maybe I zoom in a little bit. So here you see a finite element mesh partitioned into 4096 subdomains. On the next coarser level, we combine 16 of these subdomains here to form larger subdomains. And we can do this a second time, again, combining 16 of these subdomains to perform an even larger subdomain. And these subdomains, they have some overlap. That's actually what you see in gray here. This is overlap is always defined in terms of fine mesh elements. So here, I think 3 fine mesh elements was the overlap. And then we would have an even coarser level here, P0, which is always the whole domain. Maybe that's the most technical slide here. So how do we actually construct these subspaces? So for that, we need restriction operators that can restrict a finite element function to a subdomain number I on the level number L. We have a corresponding extension operator that just extends this finite element function by 0 outside of the subdomain Li. And we have a partition of unity, which is the following. So it's defined with respect to this restriction and extension operator. So we can take a finite element function, restrict it to the subdomain, apply the partition of unity. And when we now extend these local functions and sum them up, we get back the original function. So that's the definition of the partition of unity. And so now we can proceed as follows. We start with our finite element space, VH. Then we look at all the subdomains, and in each subdomain, we define 2 subspaces. So one is all the finite elements functions that have support in the subdomain I on the level L. And another space, which just consists of the restrictions of the finite element functions on the subdomains. So these functions, the blue ones, they are 0 at the subdomain boundary. You could think of Dirichlet boundary conditions. And these functions here for an interior domain are all non-zero at the subdomain boundary. So you could imagine Neumann boundary condition, or they are suitable for solving a Neumann problem. Yeah? So that's the difference between the blue and the red ones here. And then in each subdomain, independently, we solve a generalized eigenproblem in this red space, in this auxiliary space, suitable for Neumann boundary conditions, using two bilinear forms, A bar and B bar. So the A bar is essentially the bilinear form A that's restricted to the subdomain Li. So we are solving a Neumann problem here. And the right-hand side, the B involves the bilinear form A and the partition of unity. And once you have solved these local eigenproblems, your core space consists of all the functions coming from all the subdomains, for every subdomain, you take all the functions which have an eigenvalue that's smaller than some threshold eta. Yeah? So you take the eigenfunctions corresponding to the small eigenvalues in each of these subdomains. And this forms your core space. So that's basically the construction which can be done in parallel. So I skipped the theory here. So there's a rigorous theory where you can prove that controlling with this threshold eta, you get coefficient robust condition number bounds. So let me show you some results. So these are typical test problems here with heterogeneous coefficients, scalar diffusion problem with isotropic permeability. And here we first do a two-dimensional problem with a weak scaling, means we increase the number of subdomains and the number of degrees of freedom per subdomain is fixed. And now we can use different numbers of levels. So this is the two-level method, the original Genio method. So it has a robust iteration numbers independent of the number of subdomains and also the mesh size, of course. We can also now increase the number of levels, and you see there's a slight increase in the number of levels here when we go up. So we conjecture here that the condition number bound is something like O of L squared here. And we can do that also in 3D, of course. And here we already see some improvements. So you have to go to relatively large problems in order to see an improvement for the three-level method comparing with the two-level method, but starting with about 4,000 subdomains in 3 dimensions, you can see actually an improvement for the three-level method compared to the two-level method. We can also solve more difficult problem like the SPE10 problem, which is a well-known benchmark problem for heterogeneous problems. It works for continuous Galerkin, so the standard conforming finite element method, the cell-centered finite volumes, and the discontinuous Galerkin. You can use 2 levels and 3 levels, and it's basically always the same number of iterations, independent of coefficients and discretization scheme. And it also works for this carbon fiber composite problem. So that's solving linear elasticity with a highly heterogeneous stiffness using Q2 serendipity elements. And also here we have a slight increase in the number of levels when we go from a number of iterations, when we go from 2 to 3, but then it stays pretty robust when adding a 4th level here. So with that, I come to the end. I've shown you 2 approaches. One is matrix-free high-order finite elements, where you can achieve a substantial fraction of peak performance by increasing compute intensity on the one hand and reducing the number of flops on the other hand. And I've shown you some complementary approach where we can do coefficient robust solves in the realm of spectral domain decomposition methods, and where we can get scalability to large machines by having more than 2 levels. And of course, these things could also be combined. That would be the next step that we would do, is that we replace our algebraic multigrid method in the partially matrix-free method by this new domain decomposition method in order to achieve more robustness for more difficult problems. And with that, I would like to thank you for your attention.
Yes, so thank you so much. So let's thank the speaker and for his excellent presentation. Yeah, now the talk is open for the questions. So if you have any questions, you can write in the chat box.
Peter, thank you. Really masterful weaving of all these levels of the vertical tool chain, including the robustness. I was wondering, given that your background is ordinary multigrid, let's say, not the spectral multi-element, what are the prospects of handling hot order operators within a multigrid coarsening framework? It seems that most of the multigrid solvers are still working with low order element for all of the natural reasons in terms of having balance of negative diagonals and positive off diagonals and so forth. And with the high order methods, you have alternating sign, and it's harder to aggregate and preserve the effective conservation properties. So what is your direction in that?
So you mean more algebraic multigrid?
Yeah.
Because I think geometric multigrid has been done. So there's a lot of work by Martin Kronbichler on geometric multigrid methods, and so they typically use first a P coarsening and then an H coarsening. So I think what one would do is you could still do I would not directly start with algebraic multigrid on the high order system. Yeah. So I think what one would do, and I think that has been done, I think Omar Gattas has done that as well, so that you use a P coarsening in geometric setting, and that works because usually on the element you don't have heterogeneous coefficients. Yeah. So that's typically a smooth coefficient, and there this worked quite well. There's no reason for algebraic multigrid. And then for the H coarsening, you could first also have some levels of H coarsening in geometric case, but as soon as you notice the heterogeneity, you would switch to algebraic multigrid low order. I think there's no need for high order apply or AMG applied to high order.
Yes, so there is a question from chat box. So what do you suggest matrix-based versus matrix-free approach for solving general PDEs?
So first of all, this matrix-free approach, it's really general. So it can be applied to also to, of course, the continuous Galerkin method. It can be applied to nonlinear problems, to time-dependent problems. So it's not restricted to elliptic PDEs or something. Yeah. So that's one point. It's very general. The other point is, and that were these two directions in my talk, if you have a good iterative solver in the matrix-free setting, it's the way to go, I would say. But sometimes the problems are very difficult. Say in this carbon fiber composite, I would not know a matrix-free simple iterative method that can solve this problem. So there you need really robust domain decomposition methods, and these are typically matrix-based. Yeah? And also the algebraic multigrid method, as the name implies, it needs a matrix to start with. Yeah. And then there's this this game that you can do. You do matrix free on the high order part, and you do matrix based on the low order part. So at some point you have to go to a matrix. But when it works, the matrix free approach is typically much faster.
So if you don't mind, can I ask a question?
Sure.
Yeah. Yeah, so extension to the first talk from Professor David. So what is your experience with the finite element implementation on the GPUs?
Actually, none, because we have not been done something on GPUs. With respect to this matrix-free implementations, Joachim Schöber, he has done some work on GPUs as well, I think, and also on tetrahedral elements. There, I think a big problem is that the local memory is quite small on GPUs. And that is a problem. So, for example, in the sum factorization, there are these little matrices, the one-dimensional basis functions at the one-dimensional quadrature points. So we typically store these matrices and use just the entries, and they would fit in level 1 cache, yeah, or level 2 cache, yeah, at most. When you go to higher polynomials degrees, then on the GPU, you would not get them into the local memories. Yeah? And so, for example, Joachim, they have methods where they do not even store these one-dimensional basis functions at the one-dimensional quadrature points, but they would do this on the fly as well. Yeah? So, for example, when you use Legendre polynomials in a hierarchical representation, then you can get it to something like 4 flops for a basis evaluation. Yeah. And so you have to play more tricks to really get it into these small local memories. So that's the challenge with the GPUs.
Okay, thank you. So any further questions? So I don't see any questions from the chat box. Yeah, if not, so let's thank the speaker again, and really thankful to the Professor David and Peter Bastian in this session. So very exciting talks. And once again, thanks for accepting to give a talk here. So hopefully we'll see sometime in the future. So with this, we would like to close this session, and we will have a virtual coffee breaks, unfortunately not physically. And we will meet at 5:35 Indian Standard Time. And in European time, it's around 2:05. So thank you once again.
Thank you, bye.
Thank you, bye. Yeah, so Professor Eduardo. Hi.
Hi,
Hi. Thanks. So
I
can you
tried to
try
share
to
this.
share?
Yeah, I tried to share the slides just to see if they worked, and they seem to work. So
Okay, great. Thanks. So maybe in 10 minutes, we will
yeah,
we'll start the session.
maybe I'll share the slides, a couple of minutes in advance, and then so okay.
Yeah, sure. Thank you.
Nagai, we'll start in 5 minutes, right?
Right. 5:35 in 5 minutes.
Yeah, the second talk, I guess just got over. Little bit delayed.
No, but we are delayed by only 5 minutes, I guess, right?
Yeah.
Yeah, it's okay.
No, yeah, I think Eduardo is having trouble with the screen sharing, right? It's not.
I'm just every time I try. Hi, Anil. I just every time I'm trying to put it on full view, it stopped. It paused the share. I'll figure it out.
Okay. Okay. When you try full screen, it goes up.
Yes, which is strange.
You got some nice mountain background behind you.
That's where I hiked a few years back.
Not this summer.
Not this summer, no. Okay, let me try the other way around. Let me try to share to share already the thing in full zoom. Let's see if that works.
Right.
Okay, can you see it now?
Yeah, now it's fine.
Okay, so I had to first do in full view and then share.
Okay, so we'll probably start. Right. Navya, we can start, right?
Right.
Okay. Right. So it is definitely a great pleasure and privilege to introduce next speaker, Professor Eduardo Di Napoli. Eduardo and I go a long time back. We've been close friends for a long time. So it's definitely indeed a pleasure to have him speak at this small workshop that we put together for our launching our HPC center. And I couldn't think of a better person from my side to invite to give a talk. So Eduardo Di Napoli is a staff scientist at the Jülich Supercomputing Center, and he leads the simulation and data lab on quantum materials, an area that is definitely quite up and coming and interesting. The whole idea of quantum materials, of course, he will talk more about various some facets of that also. But I had requested him to give a talk that is more focused on how you can use HPC techniques, or how you can even innovate on HPC techniques to learn about various aspects of nature, ranging from materials, which is a specialty, to biology, to geology, to weather and whatnot. Eduardo's PhD was at the University of Texas at Austin, which is where we met, and he got his PhD in August 2005 from the Weinberg Theory Group. Many of you may have heard of Professor Steven Weinberg, passed away a few days back, and he was quite a titan in the field of fundamental particle physics. And Dr. Di Napoli did his PhD from there, and in high energy physics, and then was a postdoc at University of North Carolina, and visiting scientist at the Perimeter Institute for Theoretical Physics, which is again another wonderful place to be. And he is also has received the Fulbright Fellowship and the and another one from Volkswagen on computational science. And as you can see, right now he's working on quantum materials and modeling them, but he started off in high energy physics, so he has a wide variety of interests scientifically, and we'll talk about some of these things. And definitely therefore the research quite naturally is quite interdisciplinary in nature. So title of the talk today is Chasing the Hardware Evolution: Goals, Challenges and Perspectives in High Performance and Parallel Computing. So Dr. Eduardo Di Napoli.
Thank you, Anil, for the very kind introduction. Yes, we go with Anil very long back, and I have to say, I am definitely a physicist by training, and then transformed to a computational scientist by trade. in the years to come. And this was for me actually a very strange transition, because it happened at a moment where computational science was booming. In 2008, when I started working at the Jülich Supercomputing Center, you can see it, a picture of it on the right. This is a very large facility with right now more than 6,500 people. It's in the middle of the woods, a little bit like the ISCR, but this is not a tropical wood, so I would say less luxurious than your university is. But the Supercomputing Center plays a very main role into the campus. Only our Supercomputing Center, we have more than 260 employees. They work both on the hardware and the software and in between. So there is a lot going on. Now, why I'm trying to give this introduction, to give actually a little bit of an explanatory intro on what is a simulation laboratory and why we are integrated in a supercomputing center. So the idea of simulation laboratory came up pretty much when I started working in Jülich, and it's really an enabler. It's an HPC enabler in the sense that it really connects a community and to the use of these very large machines. And it became, with years, with the 10 years that followed that first intuition by our director, really a key element. And now we have our supercomputing center, more than 11 simulation laboratory, each one going from handling a different fields, from computational biology to meteorology to geophysics, neuroscience, high energy particle physics and whatnot. And in particular, the simulation laboratory I'm heading, it deals with particularly condensed matter simulations. It's called quantum materials because it does not deal with classical simulations of materials. For that, there is a different simulation laboratory. But we deal with everything that goes in very different direction in condensed matter physics. Now, what does a simulation laboratory do? Well, in general, it operates both at the method development and algorithmic design, but also goes to code modernization, so to codes that are already existing and that are legacy. It is one of the important pillars is really HPC knowledge transfer, and I will explain what I mean with that later on. And in the course of dealing with these two main pillars, it explores all sorts of it actually exploits all sorts of fields ranging from programming models, performance portability, how to exploit hybrid architectures, etc. Even to arrive to co-design. So in this sense, I'm actually very happy to come after the very nice talk of David Keyes and Peter Bastian, because David Keyes gave a really broad introduction on the field, which saves me to actually gives their bits and pieces of it. And Peter Bastian gave a really excellent introduction on HPC, which I will use here and there to explain some of the concepts that I will cover. Now, the simulation laboratory I've been heading has been existing for now about 8 years. And in 8 years, we collected a number of projects. And you can see here the main portion of them. There is the classic density functional theory, which is really the standard model on condensed matter physics. There is a number of developments on numerical linear algebra used in density functional theory. Recently, we expanded towards non-equilibrium Green's function methods, but also functional normalization group methods. And also we have some activities in data-driven materials. As a matter of fact, in the last 2 years, our laboratory, going from a simulation laboratory, expanded to be a simulation and data laboratory, where we also started using some machine learning techniques to, for instance, in the latest year, to probe the functional dependence of N-type formation for lanthanides, orthophosphates over some basic atomic quantities. So of course I cannot cover the entire range of activities that we do, and Anil actually asked me to, more than anything, to describe the techniques. So what really we do in bridging this gap between the community of condensed matter scientists and the use of the machines. And I want to say that these techniques are not specifically limited to the field that we are particularly involved in, so quantum materials, but they apply to also other fields. So while the examples that I will use come from my most close experience, these methodologies and these concepts can be applied to also many other fields. So this is the outline of my talk. I will give a very, a 10 minutes personal perspective on the hardware trends and evolutions, and what are the challenges in the simulation software and material science. Again, but not only material science, this can be also seen also in other fields. Then I will give a little bit of what I consider the 4 steps in scientific computing, and how these 4 ideal steps become actually, when they become 4 practical steps, they include much more than what the ideal steps describe. And I will give an example of that. I will use also this example later on to understand how we can go from scientific computing to high performance scientific computing. And if I have time, I will give also another example using adaptive numerical integration in functional normalization group. So time permitting, I will wrap up these lessons, and I will hope that to have conveyed some message to the starting community that you are growing in the IISER, and I hope that this will serve as a good inspiration for future generation of computational scientists. All right, so first, one short slide on trends both in academia and industry. These trends are different. I saw that tomorrow you have actually in the program a day with industry, and so I wanted to mention this. The work in the private sector and the work in the public sector are quite different. In general, in the target in the private sector is really to arrive at the product, and to arrive at the product, they have to do it in a short amount of time. So we typically, and this comes with I've been talking with people in Toyota, with the people in BASF. These are, the time frame is 3 to 6 months. And typically this is not a time frame that we see in academic research, where we have projects that range at least from 1 to 3 years, and where the focal point is really fundamental research in developing methods, in developing functionalities, and then using large-scale computation to simulate real-world materials. But these are not the products. This is a material in abstraction from the product. This is important because in the academic sector, we develop experimental codes that to arrive to become a stable and verified simulation code requires many years, and requires a community that supports it, which needs a big drive by a large community. Now, let me switch now to what is the tendency on what is the tendency in what is now hardware evolution at a large scale. So this is data taken by the top 500 list everybody can have access to this data. So, and you can see here data from the list in November 2017 and in June 2021, so the latest. I just reminded that the top 500 list is updated every 6 months. And you can see that from the left side of the table to the right side of the table, that the percentage of performance that is extracted from accelerators went from roughly 25% to almost 40%. And this percentage is going to grow. There is no doubt about it. And this is an important point because just to give you 2 examples that are close to me, because these are clusters that are hosted by the center I work in. On the left, you can see a cluster that is now about 2.5 years old. So it's closer to the November 2017, a little later. It was done in 2018. But you can see that the majority of cores is CPU cores, and this is an Intel architecture like the one that now you have in your new computing center. And the GPU nodes are limited. There are only 56 nodes with 4 B100 NVIDIA cards, but the accelerators, the amount of accelerators are limited. In the right-hand side, instead, you see the booster module. This is part of our own so-called modular supercomputing concept. But now the shift, there is a big shift. Now you see that the CPU cores are still quite substantial, but are much less in number. This is a light CPU, if you want to call it, because it's still 2 times 24 cores like the previous one. But now there are 4 GPU per node on all the nodes, which means practically the share amount, the largest amount of performance comes from the accelerators. And so you can see that even in our supercomputing center, we follow the shift from most performance on the CPU to most of performance on the GPUs and accelerators. But there has also been another trend. The other trend is the number of cores per socket. And this is another table derived from the top 500 list. And you can see that the majority of systems have at least 20, if not more, cores per socket. And this is really the tendency. And it's going to just increase. Your computing center, at the moment, you have a system of 14 cores per socket, but this trend will be increasing. And the more one acknowledges that and cope with it, the sooner it understands that the future is to try to leverage node performance as much as possible. Otherwise, the code that you will be working with will really extract minimum performance. So you really have to work on the node level before you work on the largest parallel level. And again, this is another example close to home. We have another cluster that is the Eureka DC. DC stands for data-centered module. And in this module, again, we have a fairly large number of CPU cores, but these, in this case, are much heavier. These are instead of being light CPU nodes, these are heavy CPU nodes. Now, as you see, we have 64 cores per socket, and this is along the trend that I just showed. So I've seen what is the trends on the hardware. You may feel like Calvin, and I like to break a little bit with one of my favorite cartoons. So Calvin says, given that the pace of technology, I propose to leave math to the machines and go play outside. Unfortunately, Calvin doesn't know that the more the technology advances, actually, the more we need ways for this technology to exploit the technology. And this is where the hard work stands. In fact, if I take the example of simulation software material science, but again, this applies also to computational biology or to climate science, numerical algorithms are ubiquitous in these fields. And in general, numerical libraries So the kind of libraries that, for instance, David Keyes was mentioning Scalepac and then the transition to Slate, are used really as black boxes. And this is nothing bad in using libraries as black boxes, but of course, using them as black boxes enables the fact that everybody can use them. They have the same API, they have the same interface. But on the other hand, they cannot exploit the particular structure that a certain application has. There is also a different trend, which is to develop numerical solvers as in-house. And that means practically that these libraries are deeply embedded in the software. They cannot be used by any other software. And there are examples in material science, for instance, if people is familiar with Quantum Espresso sweet code, there is inside Quantum Espresso a Jacobi-Davidson algorithm and developed in an eigensolver that solves for the eigenproblems that appears in having density functional theory computation. In BSE, so in Bethe-Salpeter equations, there are also some eigenproblems to be solved, but these are very large and usually, and so only a very small amount of the spectrum is required. And people usually use here conjugate gradient. In particular, there are codes that use inside developed Kalk-Reuter-Simmer conjugate gradient, and so on and so forth. There are several examples of that. So what are the obstacles to parallelism in HPC from these two types of libraries? First of all, as I said before, domain-specific knowledge does not influence the algorithm choice of the library. You can choose any library and uses that as a black box. And external libraries are conceived as a rigid standard interface, which is an advantage for everybody to use it, but you cannot really modify this interface to perhaps input something else to the library. On the other hand, in-house solvers, the one developed in-house, are really hard to modernize. And in most cases, they carry the curse of early optimization, meaning, for example, that they minimize memory usage versus maximizing flops. Well, sometimes some other way around, it's the way to go. And standard libraries also take time to port and modernize. And this is the same also for in-house libraries. Now, there is also a third path that goes beyond the tradition of these two approaches. And one encompasses what I described as the shortcomings of these traditional path, which is exploit available knowledge, try to really increase parallelism of complex tasks, and facilitate performance portability. In order to do that, one needs to have a flexible interface that can accommodate knowledge of the application as input. One has to have design algorithms, as already David Keyes said, to really avoid internode communication. So algorithm development really plays a key role. And really, the importance is to use that specialized low-level library to maximize the extraction of node performance. So we cannot expect that everybody is a ninja coder to really extract node performance, especially when nodes are increasing in size. As I said before, then the core per socket are increasing. So we really have to rely on specialized libraries developed for that purpose. And then definitely as a fourth element, we need a stable development team, which supports and quickly ports the core kernels to the latest platform. And that is a core element to really facilitate performance portability. Okay, now let me, now this is a general overview, and I want to give a more specific example of how these two traditional approach and this third approach can be exemplified, sorry, not exemplified, but envisioned. And but in order to do that, I want to give a very quick overview of the structure of scientific computing, because this will give me an excuse to explain how knowledge is extracted from an application. So these are the 4 idea steps as I envision them. This is coming from a person, as I said, that comes from working with pen and paper, and doing no computation, to actually being exposed to scientific computing in the last 10 years. So really, one starts when develops one develops something that goes through a computation to deliver scientific impact. It starts always from the mathematical model, and then from the mathematical model, the big jump is to actually implement software, implement the code, do some computation with this code, and then derive scientific impact. These are 4 ideal steps. In practice, especially the first 2 steps are much more than that. For the mathematical modeling, in fact, one has to first design the algorithm. Mathematical modeling and design algorithm are not an automatic step. You have to really put effort in designing the right algorithm for the mathematical model you have. Every mathematical modeling has many different algorithms that can be used to implement, to realize it. When you go to implementation, one has to take in consideration programming paradigms. So which language you're using, which parallelization strategies you're using, which kind of hardware you're using to computing. And then all this is translated in an implementation. And for it, if you change computing architecture, the implementation changes. And the parallelization strategies may change also. So these are 4 real steps. But I would like to go one stage beyond that, and say that a step forward is really a knowledge-based practical steps. And when I say knowledge-based, I mean that it's important that the high performance computation, they do not only come from a clever use of programming paradigms and parallelization strategies, but also from the ability of extracting and exploiting information that comes from the application itself. And these can influence the algorithm design and also influence the programming paradigms and parallelization strategies. Now, I want to use the next example to explain how extracting and exporting information from the performance computation influences the algorithmic design. So this part here on the right-hand side. Then I will give an example how now it actually influences also the parallelization strategies. But let's start with the algorithm design. So in density functional theory, which is, I said before, for whoever is not familiar with it, is really the standard model of condensed matter physics, especially when you have to solve the Schrödinger equation. Density functional theory is organized roughly as a self-consistent cycle. So you start with a number of equations called Kampf-Sham equations. These are just a way to describe the many-body Schrödinger equation in terms of a one body, because it's based on the charge density. This gives rise, once it's discretized, to solve a set of eigenproblems. And these eigenproblems depend on so there are many of them depending on the index L, because this index L says it specifies the number of cycles. And then it depends also these other index that you can think of them as a momentum indices, but there are also discretization in space. So this can be also thought as discretization in space indices, and so on and so forth. Once you solve this set of eigenproblem, one computes a huge charge density, so the density of electrons practically, and that compares to the initial charge density. And if this difference is below a certain thresholds, one declares the self-consistent cycle converged. Otherwise, this repeats itself on and on and on. I am giving here an example of a specific realization of density functional theory called LAPW. This is not really important. What is important is that these eigenvalue problems are all dense, they are generalized, and they are Hermitian. And usually what is needed is about 2 to 10% of the lowest eigenpairs. Now, how big are these problems? In general, they are typically between 10 and 50,000 big. Size of these matrices. They can go up to 150,000, 200,000, in some cases even larger. How are these solved? So the idea is that you add a certain iteration of this self-consistent cycle I showed before, this cycle here, as I showed before. So for one index cell, one solves each of the problem with a direct solver, usually ScaleAPAC, typically, finds the solution, then this solution are used to complete the cycles, and the next cycle, one solves it again. In the mathematical model, actually what is really difficult to extract is that each solution contributes to the problem, to each of the problem in the next cycle. So there is no really a clear correlation between one solution and the next, and the solution and the next problem. In practice, by looking at the computation, actually, so a posteriori, one finds that there is such a correlation. There is a correlation that as these index cell progress, connects a solution on one index cell to the solution on the index cell plus one. This, we unravel this correlation, and we use it with an iterative solver, which allows us to take the old solution and input it into the solver. So practically enlarges the interface of the solver, and the solver can take advantage of this knowledge and speed up the solution. In practice, this has been realized in a code that has many different other features, because it is written in modern C++ with an interface that practically separates the algorithm from the implementation. But what is important, and I will show these results of the code, is that by inputting the old solution to the new one, we see a speed up in the performance. So for already at index L equal 2 up to index L equal to 25 in this particular simulation of a compound of gold and silver, you can see that there is a speed up that goes from 2 to 3.5 just by inputting the solution. I'm not even talking about parallelization here. You have to imagine this speed up is purely sequential. Okay, so this is what I mean with extracting and exporting information and choosing a different algorithm to actually solve the problem. Now, let me go a step beyond and now talk about high-performance computing. So what is now let's say the structure of taking an existing algorithm or an existing code and make it high performance? And here I am taking the two steps that are previous of the 4 steps that are previously described and expanding them a little bit further, looking at the part where I had the mathematical model and the algorithm. You can see that the algorithm optimization actually is made of really 2 parts. One is really restructuring the numerical operation within the algorithm, and the other one is rearranging the data structure. And then the parallel implementation comes from really understanding which are the low-level kernels that one needs to use on the specific architecture that one uses, and separates the data from the algorithm itself. Now, what is really important here is in the greased box on the left, which is the fact that performance comes from both node level testing and cluster-wide testing. With node level, I mean really the node level of which of the cluster, and then cluster-wide when you actually execute the entire computation using more than one node. So typically using an MPI interface, MPI API. All right, so why it's important, the node level performance? And I will focus on this example on that. Because as already explained, there is a hierarchies of memories. And these hierarchies of memories has become more and more extreme as time passes. In fact, as this is a simplified model at the moment, for instance, for the AMD EPIC-ROM CPUs, which are the the one that are at the moment installed in the newest supercomputers, you have the L3 cache, for instance. There is not only one L3 cache per socket, but there are multiple L3 cache per socket, and these are organized in NUMA domains. So now, before, typically each socket had one NUMA domain only. I'm going a little more technical here. I apologize for that, but just to give an understanding that now, for instance, in the Eureka DC module, which I briefly outlined before, these supercomputers have 8 NUMA domains with two sockets, and within each socket there are 4 NUMA domains instead of the classic 1 or 2. And this complicates things. And remember, this computer also has 4 GPUs, and to access these GPUs properly, actually one has to really connect one GPU to a specific NUMA domain, so that there are 4 out of these 8 NUMA domains which have preferential access to these GPUs. So as you can see, things complicate quite a bit. So how do we make these, the Chase algorithms that I showed before, we implemented to take advantage of the information and really try to extract the best possible parallelism. First of all, we try to do computation redundantly. As David Keyes already explained, it's important to communicate the little as possible. So this is the algorithm of the Chase eigensolver. It's not really important to understand how the algorithm goes. I just want to point out that the brown part of the algorithm are the one that are executed in parallel over many nodes, and the one in red are the one executed redundantly on the node, which means the one in red, this QR decomposition, the solution of the reduced eigenproblem, and the back transformation, these are done by each node independently. And one expects to actually each node to recover the same result. Now, how does this reflects on the performance of this algorithm? Now you can see here, it's important to actually test, or either test with a sweet spot analysis, or even going with heuristics, but it's always better to test. And here you can see the same algorithm colored in brown and red, and you can see that in logic would command that the more cores so the more tasks, the second column are the tasks per node one uses, the more the time should go down. In practice, for instance, let's look at the RR part of the Chase algorithm. One observes first a decrease in time, but then an increase as the number of tasks per node becomes larger, to the point that it's absolutely inconvenient to use very large number of tasks per node. There is a sweet spot indicated by this green row, and this is either the same if we use one node only, or if we use 16 nodes. There is always a sweet spot in the way we're using the nodes at the and when we compute redundantly certain part of the algorithm. So I want to really emphasize that this is extremely important when you want to really optimize the algorithm for parallelism and performance. And just I just want to show that the same algorithm scales really well over many different nodes. These are number of processes here are number of MPI processes. There are 4 MPI processes per node. So you can see here a strong scaling both in CPU and GPU. So we were able to port, so our eigensolver is ported on GPU, but it can also work on CPU. And when I say ported on GPU, it doesn't mean that it uses only GPUs. It keeps using for the lowest part, the CPU part. So it really is a hybrid code. And this is thanks to the fact that we separated the implementation from the algorithm. I don't have time to explain that too much, but perhaps if people want, I can answer that in the questions side. let me. I just want to give you in the last remaining 5 minutes a different example. I will be very quick here, but just to give an idea of how this approach can be applied in a different field. This is a functional normalization group, which is a rising star in the field of condensed matter physics, and it's a rising star in the sense that now is really approaching the point where you can return physical results that are comparable to the one in other fields for condensed matter physics. What's important here is that this is a set of equations, and the most expensive part is in this integration here. And here is explained in these schematics. 80% of CPU times goes in performing this two-dimensional integration. And the code that we were looking at, this TUFRG, it's a code that practically evolves. These equations practically are parameterized by parameter omega. As these parameters evolve, this integration goes from something fairly smooth to something very non-smooth. And so it requires something that is adaptive in nature. Let me just skip on this particular case, but just to say that this code was using a library called DCU-HRE, which is an adaptive integration. This is written in Fortran, and was working fairly well, but it was not really optimized for exploiting node level performance. We practically took we took a similar algorithm, not exactly the one from DCU-HRE, but we use a Klein-Shou-Curtis algorithm for numerical integration, and then we designed it and parallel optimize it so to extract the best node level performance. You can see this is the results that are 3 years old, but you can see for a number of threads, these are a machine that had 24 cores, so, and then some hyper threading to go to 48 threads per node. But we are up to 24 threads, almost close to ideal. And this practically reduced 1 order of magnitude the amount of time to do function evaluation. So to conclude, in the last 2 minutes, in the lessons learned in the last 10 years that I hope can be useful for the new Center of High Performance Computing that you started at the IISER, is that exploiting domain knowledge, it's really important and can accelerate computation. And I give you an example of that today. Having a flexible abstract interface separating algorithm from implementation also facilitates a lot of porting portability, performance portability. I didn't give an example of that, but this is a lesson that we learned. Extracting node level performance using specialized kernels is not trivial, but you really need to use specialized kernels. In the example I gave you, we used specialized kernel from a DCU solver for GPU implementation, and from the BLIS library, which is a library that implements BLAS. It is developed by the University of Texas. And fourth of all, avoiding communication also comes at the cost of increasing memory usage and decreasing parallelism. But one needs to strike a careful trade-off between the increase of memory usage and the decrease of communication. There is always a sweet spot, and this is not easy to find, but this is the only way to really advance applications in the future of computational science. Thank you very much for having listened to me, and I hope this can be useful for a future generation of coming computational scientists.
Yeah, thank you so much, Eduardo, for that wonderful talk. And let me see if there are any questions. If there are any questions, please ask or put them in the chat box. While people are probably bring it up.
Um,
Yeah,
Is it,
Yeah.
can I ask a question?
yeah.
Yeah, so thank you so much for a nice presentation, Eduardo. And I have a question regarding the iteration speed up. I mean, I was a bit surprised that the iteration, if I imagine that the same solver,
Mhm.
but let's say the iteration count increases, so what could be the reason the speed up increases?
So the iteration, so the number of iteration is the same as in the, what I didn't say is that in the same number of your iterations, the density functional theory computation arrived to convergence. Okay, so the 25 iterations are the same as if you use a traditional solver, as if you use our improved solver. But because we use information from the solution of the eigenproblems at the previous iteration, we reach convergence in much less time. The fact that it increases is because practically the vectors. So imagine this vector solution of this eigenproblem. These vectors for the previous problems are not so far from the solution of the next problem as a random vector that is used as any random vector. So by using these vectors that are somewhat already a little bit oriented towards the solution, the algorithm takes advantage of that and makes much less computation. The key here is doing less computation to wrap the solution.
Okay, thank you.
So you had mentioned about this finding the sweet spot for those algorithms. I guess I didn't get whether that is that has to be done for every problem or for the algorithm itself. No,
it has to be done for the algorithm itself, not for every problem. So it has to be done for the specific architecture. So once you want to use this particular library on a specific architecture, you need to understand what is how best use the library in the architecture. As a matter of fact, we are developing a heuristic library, a heuristic script in Python that helps the user before running actually the solver to find out which is the best configuration to run it. But I show to you that what I show is an example of doing that by really actually running it and doing the sweet spot analysis directly, because that is really the most precise way of doing it. One can also do some heuristics, but sometimes heuristics do not tell the full story.
Okay. Yeah, but then if you are using the code developed by somebody else, then understanding how to find the sweet spot is going to be a challenge, right?
So this is one of the reasons why the library has as an accompanying Python script, which means practically every user do not need to understand the intrinsic working of the library. Definitely, it doesn't need to do that. On the other hand, of course, if a user is interested to use this Chase eigensolver on, for instance, your cluster that has 14 cores per socket, once he has find the sweet spot once, he will always use the same configuration. So maybe there is a little bit of work at the beginning to run different configurations to see which one is the one that performs best. But once that is done, and this can be done in many different ways. One can do it by hand, but for instance, we didn't run 100 different simulations to find that. Actually, we used something called a Joub environment, which runs repeated repetitions of these of the library for different configurations at once, all at the same time, and then we extracted. So that practically costed us a couple of hours, and on compute time, and that was done. Right. For the inexperienced user, it may cost maybe a day, because it done by hand. It takes many scripts to be configured by hand, but it's not that expensive.
Okay. So are there any other questions? Nagesh, can you see if there are any other questions?
So I don't see any further
Okay.
questions on the chat box, I think.
Okay, so let's thank Dr. Eduardo Napoli once more for this wonderful talk.
Thank you very much for having me.
Yeah.
It was a pleasure.
Thank you. Let's we'll go on to the next talk. Right, Nishant?
Yeah. So Bertrand,
Yes.
yeah.
Can you hear me?
Yeah, sure. Yeah. Okay. Hello. Yeah, Bertrand, I think the audio is stuck.
Right?
Yeah. No, we are able to hear. Yeah.
Okay.
Okay.
Is it, are we starting now? Or?
Oh, okay. So I will just briefly introduce you. It is my pleasure to introduce Professor Bertrand Laurent, who very kindly accepted to give this talk at this meeting. So Bertrand did his PhD in 2011 from the Pasteur Institute. He worked with Professor Bernard Dujon on functional and comparative genomics of the budding yeast. As you all know, genomics work also requires a lot of high throughput computational analysis. And he moved on to the laboratory of Professor Lorraine Symington at Columbia University to do his postdoctorate on understanding the mechanisms of homologous recombination in yeast as a model system. So since 2007, he's at CNRS in France, and he's basically working on genome dynamics and recombination, where he's trying to understand the molecular mechanisms of homologous recombination in yeast, both during mitosis as well as during meiosis. So his lab extensively uses these next generation sequencing methods to analyze recombination data in yeast. And this kind of analysis also involves the use of high throughput computational methods. So Bertrand is going to give us the perspective about using computational biology, especially involving HPC, in analyzing recombination in eukaryotic model organisms. So Bertrand, you can share your slides when you are ready.
Can you hear?
Yeah, we are able to hear, but not your slides. We are not able to see your
Okay.
slides.
Okay. Can you hear me?
Yes, we can hear you.
Start now.
But I think you have to, yeah, we can see your slides. Yeah.
So yeah, okay.
Yeah.
Yeah, am I inter?
Yeah.
So
Okay, the voice is a little bit breaking. Yeah, but yeah, otherwise we are able to see the slides.
computation, and so it's somewhat different talk that you could see. It will be simply an application of high performance computing.
Okay. I did that.
Oh, sorry. Okay, now it should be okay. Is it okay?
Okay, yeah. Okay,
Okay.
let me see. Yeah, 1 minute.
Yeah, is it okay now? Sorry.
Yeah, it's fine now. Yeah.
Okay, sorry about that. And I'm sorry. I'm somewhere in the middle of nowhere. Sorry about that. Okay, so if you hear me, I can start. Okay.
Yes, it's fine. Yeah.
Okay, so as I was saying, so the talk will not be so much about high, but it will be about the application of high performance computation in biology. So, okay. So the overview of my talk following will first introduce you DNA ethics to biology. My topic, homologous recombination, and initially I thought I was going to study of recombination, but eventually our topic, which is going to be the this is just easy. Yes. Yes. Okay, so sorry. Can you see my?
Yeah, we are not able to see the slide.
Okay, my
Yeah,
you can't see my slides?
Yeah, it's fine now. Yeah.
Things. Two complementary DNA strands.
Hi, Nishant.
Yeah, I think he's having some connection issue.
Okay.
He try calling.
Okay, I hope I'll be able to go through. Okay, so I'll start. So I'm going and okay, I'm really.
Yeah, now it's audible.
Yeah, so I'm okay. So I was telling you that so since the discovery of the DNA structure, so the current status of the DNA biology ended up in the full sequencing of different organisms, and the first organism to be sequenced has been Haemophilus influenzae. It's a bacteria. It's about 2 million bases long, so 2 million repeats of ATGC. In 1996, the first eukaryotic organism has been sequenced. Is the baker's yeast, my favorite model. It's about 12 million bases. Then the first multicellular organism, so it's a worm, Cenorhabditis elegans, has been sequenced. It's about 100 million bases. And then the first insect, the first plant, and the human genome. Only a draft of the human genome has been fulfilled in the year 2000, and it's about, as you probably know, 3 billion bases. Have to have in mind is that all those sequences have been done using very tedious methods, and it took many years to achieve the sequence in the full sequences of those genomes. And in 2007, there was really a revolution by the next generation DNA sequencing technology that now allows to generate the full sequence of those genomes in only a few hours or a few days. Those next generation DNA sequencing allow the generation of sequences of 100 bases long, and using a single run of sequencing, you generate between a few millions to a few billions of such sequencing reads. So we are now facing we could call a genome invasion. Okay, every day new genome sequences are released and have to be analyzed, and obviously require a strong computational devices. So, and illustration of this genome invasion is illustrated by this graph here of the $1,000. The sequence, a lot of sequencing reads they generated randomly, and here cover the entire sequence, but they come in computational the assembly of on the overlap of computational, because the number of bases. one short map genome. It's highly demanding in terms of computational. To generate use another nation strategy reads of several kilobases and in
Okay, since Professor Bertrand is having some issues with the internet, we will just have a tea break now, which was originally planned for around 7:10. And in the meantime, we will get him back, and then we can start at around 7 o'clock. Yeah.
ചുറ്റുമ്പോ അവിടെ കളർ ചെയ്യാണ് അച്ചു ഇവിടെ ഹാളിലുണ്ട് ചുറ്റുമ്പോ ഇതിനടുത്ത് കളർ ചെയ്യാണ് അച്ചു ഹാളിലുണ്ട് അച്ഛനടുത്ത് ഞാനുണ്ട്
Okay, I am so sorry about that, Nishant. Can you hear me?
Yeah, Bertrand. So I got your slide.
Okay.
So what I can do is I just announce that we will have a small break until 7:10 or something while we set this up.
Okay.
Yeah. So what I will do is let's see if we can get this going. I'll just share these slides. So I guess the slides are visible.
Yeah.
Okay. So then, yeah, I can basically run the slides.
Okay.
Yeah, while you talk.
Okay, that's perfect. And
right. Yeah. So okay.
So you made a break, right?
Yeah. So we just gave a small break until 7.
Okay. Okay.
7. Yeah, for another 10 minutes, basically. Yeah.
Okay. Yeah. I'm sorry again. So I'm.
Oh, no problem. Yeah, that's fine.
It's a bit stressful for me. I had to change from one house to another one. It's
okay.
just
Okay. Yeah.
Anyway.
Yeah, I think this should work. I think I can just run the slides.
Okay.
So that should be fine.
I think I will not turn on my video just to keep the the connection optimal.
Yeah, that should be fine. So Nagia, we can start in 5 minutes, I think. Or...
Yeah. So probably 7:05.
Yeah.
Okay, maybe we'll wait 5 minutes and then we can start.
Okay, we'll start, Nagia.
Yes, yes.
Yeah. So, Bertrand, yeah, you can begin.
Yes. Okay, so shall I start over again entirely, or?
Yeah, maybe we can start from. Yeah, I think. Okay, I think you had covered. Okay. Yeah, I think from here.
Yeah. Okay.
Okay.
So okay. Okay, so I was just reminding everybody that the DNA is composed of 4 bases called adenine, guanine, cytosine, and thymine. And the DNA molecule is a double helix where each DNA strand is one DNA strand is complementary to the next one, and the 2 strands are connected by weak bonds where thymine binds to adenine and cytosine binds to guanine. So next slide. So since the discovery of the structure of the DNA, the sequencing effort ended up in the sequencing of full genomes. The first single cell organism to be sequenced was the bacteria Haemophilus influenzae in 1995, followed by the first eukaryotic single cell organism Saccharomyces cerevisiae. This is the Baker's yeast, and that's my favorite model. It's about 10 megabases long. Then the first multicellular organism to be sequenced was Cenorhabditis elegans, followed by an insect, a plant, and eventually the human genome in 2000. And in 2007, there was really a revolution in the field of DNA sequencing, which is the emergence of novel technologies that allowed to sequence complete genomes almost in a single or a few runs. As you can see, a single run generates millions to billions of sequencing reads of about 100 base pair long. This can be considered as a genome invasion, since almost every day new genomes are released in databases. And as an illustration of this genome revolution and invasion, it's the evolution of the cost of the sequencing of a human genome that dropped from several orders of magnitude, from $100 million in the early 2000 years to almost $1,000 nowadays. So next slide. So the next generation sequencing technology consists of generated millions of reads of about 100 base pair that cover randomly an entire genome. And the first challenge in bioinformatics is to map those sequencing reads on a reference genome and to assemble those sequencing reads together. So next slide. So once the reads have been mapped, well, this can be done independently, but once you map the reads and you assemble the reads, you end up with what we call contigs. Those are assembly of sequencing reads together in bigger pieces of DNA. But in most cases, those pieces of DNA, they do not cover entire genomes or chromosomes. They are still full of gaps. And to fill those gaps, next slide, we use complementary sequencing technology that now generate long reads of several kilobases long that can make the junction between one contig and the next to eventually lead to complete chromosome with no gaps. And as you can see, okay. So now the DNA, it's a double helix, and it harbors the genetic information. And this genetic information needs to be expressed. And to be expressed, the DNA undergoes what we call the transcription that transforms the DNA into an RNA molecule. And this RNA molecule is going to be read by ribosomes to generate proteins. And the level of expression of a given gene reflects the importance of a gene in a specific condition. So after the expression of a genome, the genome also needs to be transmitted from one cell to the two daughter cells that emanate from a given cell by cell division. So to be transmitted, the DNA needs to be duplicated. And the DNA is duplicated by what we call the replication. And from one, so when one DNA molecule is replicated, it generates two newly generated DNA molecules, but each of those DNA molecules is composed of one parental strand and one newly synthesized strand, as illustrated here by the dotted strand. And the next generation sequencing technology can be used to study replication, because if we start from a synchronous cell culture, the DNA content from the culture before replication and after replication is going to switch from one end DNA content to two end DNA content. So next generation sequencing technology revolutionized the way to study DNA replication. And last but not least, and that will be an important topic of the talk later on, the DNA can recombine, okay? If you imagine the DNA of a single individual, it's each of us have one paternal genome and one maternal genome that comes from the fusion of the two gametes that is the basis of our generation. And if you imagine one red and one blue genome, when one individual is going to generate gametes, those genomes are going to be shuffled again by what we call the meiotic recombination during gametogenesis. And this mixing of the red and the blue genome is going to generate what we call the genetic diversity, and it's essential for evolution. Next slide. So the application of next generation sequencing technology can be applied to any field that involves DNA. I mentioned previously that it can be used to follow replication, but the starting point of really genomics is to follow polymorphism within population. The sequencing of full genomes allow us to evaluate the diversity that exists among population. And this diversity can be a diversity of the primary sequence. It can be differences in single nucleotide polymorphisms, but it can be also bigger differences because a large fraction of our genome is composed of long repeated sequences, and changes in the number of repeats of such sequences is very frequent and can have functional implications. Next. So any DNA transaction can be studied using next generation sequencing technology. I mentioned replication, but it's also true for recombination. Once we have the complete genome sequences of diverse genomes, we can easily map recombination breakpoints where mixing between two genomes occurred. Next slide. And something very powerful also linked to the next generation sequencing technology is the fact that we can co-purify proteins or any molecule when it's associated with DNA. We can simply amplify the DNA associated with a given protein that can be a transcription factor or any other DNA binding protein. And by co-purifying the DNA associated with it, we can monitor at once where such a protein binds a specific genome. So we can find all the genes regulated by a specific transcription factor, or the binding of a specific protein can be restricted to a single locus in an entire genome. This is what we call the chromatin immunoprecipitation sequencing technique, or ChIP-seq, which is really widespread. And last but not least, as I mentioned earlier, the next generation sequencing technology allowed to make a real breakthrough also in transcriptomics, which is the analysis of the expression of a genome by the sequencing of the RNA molecule generated after transcription, either directly or indirectly. Next. So, okay. So the second part of the talk is a brief introduction on the homologous recombination mechanism, which will be studied more deeply with the next generation sequencing approach. So next slide. So the simple view of recombination is the following, starting from two different genomes. When I say different genomes, I mean polymorphic genomes, where the level of polymorphism can be in the range of one single nucleotide polymorphism per 100 nucleotide. And such polymorphic genomes are symbolized by a red DNA molecule and a blue DNA molecule. And after recombination, we can see that after recombination, we have a reciprocal exchange of the red and the blue molecule. And this is what we call in biology a crossover. And such crossover can be easily mapped when we sequence the entire DNA molecules. Next. So the recombination property the homologous recombination pathway before mixing genomes, it's before all, it's a DNA repair process that starting from a DNA lesion, which is very frequent. The DNA is it's a macromolecule that undergoes numerous damages, and those damages have to be repaired accurately. And the recombination pathway is a DNA repair pathway that ensures genome integrity. But associated to recombination, there can be some level of genome dynamics, notably through the crossover that I just mentioned before. And when such crossover occur during the generation of gametes, it leads to the evolution of the species. But when those crossovers, they occur in somatic cells, like in human, they can be the source of genetic diseases such as cancer. Next. So here, the blue and red structures represent entire chromosomes. And on the red chromosome, I illustrated a DNA double-strand break. So it's a break in the DNA molecule. And this break can be repaired simply by religation. This is a process that I'm not going to talk about now. But this break can also be repaired by recombination. And the essence of recombination is to find a homologous partner and to copy its genetic information. Here it will be a blue chromatid, and to transfer the blue information at the initial break site. So you see on the left, there's a little piece of blue information into the red. This corresponds to the unilateral transfer of information from the template chromatid to the initially broken chromatid. So this non-crossover pathway is the main somatic repair pathway, but in meiosis, there's very often the generation of a crossover associated to the recombination process. In meiosis, this crossover process ensures accurate chromosome segregation, but also the generation of diversity. But in mitotic cells, this is extremely dangerous because it can generate what we call loss of heterozygosity, where you see here in the product, the cell product, there's a region which is blue on the two chromatids, and the heterozygosity initially present in the cell is lost, and it can generate the expression of recessive alleles. This is extremely dangerous in somatic cells. Next slide. So in mitosis, the recombination process is mainly meant to repair lesions that occur during the S phase, where DNA is replicated. But in meiosis, the homologous recombination process is mainly responsible for the repair of a specific cellular program started during the prophase of meiosis, where the protein SPO11 is going to generate hundreds of breaks throughout the genome. And the rationale for this is to generate crossovers that are going to generate, those crossovers are going to generate physical forces between homologous chromosomes, and those forces will participate to ensure an accurate chromosome segregation at the first meiotic division. But on top of this physical property, the crossovers, as I told previously, also ensure the generation of diversity by mixing the red and the blue information as represented here. Next slide. So here, it will be a bit technical, but hopefully the animation that is going to follow will make the recombination process quite simple. So here we are looking at two DNA molecules, okay, with the two complementary strands. The red molecule is broken, and now after the animation is going to be started, you'll see how recombination proceeds. So if you can start the animation, just one click, and that's so. After break formation, there is single-strand DNA formation that allow the search for homology, the initiation of DNA repair synthesis from the red to the blue chromatid, and then the intermediate is simply undone. And the newly synthesized strand, the dotted blue strand, pairs to the second end of the break and gives rise to a non-crossover. So this is the essence of recombination, where a key step is the second step on this figure, which is the search for homology driven by what we call a recombinase, and the canonical recombinase is RAD51. So it allows the finding of homology throughout an entire genome that can be billions of base pair long. But in this recombination scenario, we do not generate crossovers. So this is the main mitotic recombination pathway. And on the next slide, I'm going to show you how we can make crossovers, notably in meiosis. So at this step, instead of dismantling the recombination intermediate, the recombination intermediate is going to be stabilized. If you can click. So the stabilization is made by annealing of the display strand of the bubble here to the next slide of the DNA molecule. And now we have two DNA molecules that are tightly linked to one another. And this physical link needs to be removed before cell division. So to remove those links, we can cleave them. On this animation, we see that the two DNA junctions have been cleaved. The two strands of the junction have been cleaved the same way on the left and on the right. This gives specifically non-crossovers. Okay, next. Okay, we have non-crossovers, but now if we cleave the two internal strands on the left and the two external strands on the right, we specifically generate crossovers. And this is how crossovers are generated both in mitosis and in meiosis. But since crossovers are highly detrimental, even when the cell generates these complex intermediates, those complex intermediate can be also undone simply by isomerization. Okay. This is so this last step of dismantling such intermediate underscores how deleterious crossovers can be in mitotic cells. So next slide. Okay, so now that you have the basics of the recombination process in mind, I'm going to show you how we can use high throughput genome sequencing technology to understand better the mechanism of meiotic recombination. So next slide. So if you remember all the pathways I've just mentioned to you, so on the left, there's the first non-crossover pathway. And you can see that what is circled with a black dotted circle here is the final product of the reaction. It's composed of a dotted red line that comes from the template. And this red information is now present within surrounding blue information. And the red-blue piece of DNA is what we call a heteroduplex DNA. And the structure of this heteroduplex DNA is different from the pathway on the left that correspond to the first non-crossover pathway. Is different from the pathway completely on the right, where instead of having only one heteroduplex DNA, we have now two close by heteroduplex DNA. The left one is blue on top, red on the bottom, and red followed by a red piece on the top and a blue on the bottom. And in the middle here, you can see that the initial double-strand break repair model that is almost 40 years old now suggested that both crossovers and non-crossovers specifically came from the cleavage of the double holiday junction intermediate present in D. Okay, and the structure, the heteroduplex DNA present in this intermediate for the non-crossover, it's meant to be one heteroduplex DNA on the top chromatid and one heteroduplex DNA on the bottom chromatid. So basically, yes, here. So basically we have, for the non-crossover, we have three different possible configurations. And we could actually test the prediction of all this model using the approach I'm going to show you now. So next, sorry. Okay, so to follow recombination genome-wide, what we do is we take a blue and a red yeast strain that have, when I say blue and red, it means that they are polymorphic strains. They have about 1% sequence divergence. And we cross those strains and we induce meiosis. And we induce meiosis after having knocked out a specific enzymatic pathway, which is called the mismatch repair pathway. The mismatch repair pathway repairs heteroduplex DNA to remove any mismatch, because mismatches are not meant to be present in a DNA molecule. And the fact that we inactivate the mismatch repair pathway allows to stabilize the heteroduplex DNA, okay? And to analyze the structure of the heteroduplex DNA, what we do is to micromanipulate yeast cells after they underwent meiosis. So from one diploid cell on top of the figure, we end up with 4 spores. This is the typical meiotic product. And because the analysis of the structure of the heteroduplex DNA is quite hard to perform at the tetrad level, we go one step further and we separate for each spore the mother from the daughter cell to have purely clonogenic DNA molecules to analyze. So what we do is we sequence the genome of those 8 cell population coming from a single diploid cell. So those 8 different cell populations correspond to each of the 8 DNA molecules involved in the recombination process. And on the next slide, there's the representation of a typical result where starting from 2, so here we have 4 DNA molecules represented, each with 2 DNA strands. You have to imagine that the starting point was 2 fully blue chromatids and 2 fully red chromatids. And this is the result of meiotic recombination. The blue and the red information has been completely shuffled. And you can see that the blue-red transition are completely symmetrical. And those correspond to the crossovers. And here we have more than 10 crossover on a single chromosome. Obviously, the red and the blue information correspond to many single nucleotide polymorphism. And we can zoom in this polymorphism. Next slide. And when we zoom in this polymorphism, we have about 50% of the non-crossovers that show this specific pattern where we have a single heteroduplex DNA embedded into pure, here it's purely blue information, where within this blue information, there's a small spot of red-blue information. So this corresponds to the first non-crossover recombination pathway that I mentioned to you. And we can zoom in further, and we realize that in about 1/3 of the cases, we see that the heteroduplex DNA configuration is not as simple as previously, but now we have 2 tracks of heteroduplex DNA. And this is reminiscent of the second pathway that I mentioned to you that correspond to the dissolution of Holiday junctions. Okay, so next slide. So the conclusion of this approach is simply the following. In black in the middle of this slide, there was the canonical model that was the main model present in any textbook for many decades. And a simple analysis made using next generation sequencing allowed us to revisit this model and to show the importance of alternative non-crossover pathways that are represented on the left and on the right. So next slide. Okay, so here is just to show you that, so all these pathways, they also have predictions in terms of the location of the initial break. And next slide. So the initial break can be monitored because so the location of the initial break can be identified in our recombination product because we have also data corresponding to what we call SPO11 oligos. Basically, SPO11 is making breaks throughout the genome. And when it makes a break, it's released from the DNA associated with a piece of DNA covalently attached to it. And this piece of DNA is a signature of where SPO11 cut the DNA. And you can see on the graph on the bottom left of the figure here that we have sequencing reads associated to SPO11 specifically next to the position 310. So it's basically represented by the green bar, sorry, the gray bar where the SPO11 sequences were attached, and it's where SPO11 cut. And we see that the cleavage point of SPO11 corresponds to the place where we expect it to be from the model. And overall, there was a good correlation between the regions that were broken by SPO11 and where we expected them to be. So you can skip the rest of the slide because it's just an illustration confirming that for any pathway, we could have a good fit between what was expected and what we saw. And on the next slide, again, here there is the expectation of the SPO11 break on the gray zone. It should be really adjacent to the heteroduplex DNA, but in some cases, in some cases we could see that the location of the SPO11 break was away from where it was expected to be. And to explain that, we could infer some what we call template switching, which is it's very technical, but it's just to show you that when we dig really hard, we start to find things that diverge from the expectation. And basically what's going on here is that instead, when you have a broken chromatid, instead of going right away into the homolog, it starts to go into the sister and only subsequently to the homologue. Anyway, it's quite technical, but it's just to show you that such approaches allowed us to refine our understanding of the recombination pathways. And on the last slide, so this was the starting point of our study, and the endpoint of our study, next slide, shows that starting from quite static models, we could identify some new and unexpected dynamics of the recombination intermediates, which applies to both the non-crossovers, but also to the crossover pathway, okay? And so just to end up, I just want to emphasize on the absolute need of of strong bioinformatic resources to modern biology. This applies to the field of genome stability and evolution that I mentioned here, but it also applies to any biological field that relies on imaging, or almost any biological field now relies on bioinformatics and high computation resources. So, and on the next slide is just an acknowledgement slide. Sorry, I skipped it. I just wanted to acknowledge my collaborators, but I'm done and I can take questions if there's any.
Yeah. So are there any questions for Professor Bertrand? Okay, let me start. Can you hear me?
Yes, sure.
Yeah, okay. So you basically mentioned that as per the old model, the heteroduplex should be on both the strands, right?
Yes.
Whereas you see it in one of these strands at a certain percentage.
Yes.
So I was just curious about that percentage. So your model predicts it should be there most of the time. And I mean, is the percentage you are seeing consistent with the model?
So if I understand correctly, what you're asking is, yeah. So the percentages that I gave were initial estimates, and after we refined those estimates. And what we can say is now that the main pattern is actually the trans heteroplex DNA pattern, where you have two heteroplex DNA but on a single chromatid, and the presence of heteroplex DNA on two chromatids significantly increases in some mutants of in some ZMM mutants that you obviously know. We increase the presence of heteroplex DNA on both chromatids, meaning that basically what's happening is in some mutants you interfere with the crossover formation, and what was meant to be resolved as a crossover is now resolved as a non-crossover by structure-specific nucleases.
Yeah.
But the fraction of events with two heteroplex DNA on two different chromatids is really minor under normal conditions.
Okay. So you mentioned you get it around 48% of the time, right, on one chromatid.
Yeah.
Okay. But your model shows it should be there most of the time, is it?
Yeah. So the actual view is that you either have a single heteroplex DNA or two heteroplex DNA on a single chromatid. You have that more than 90% of the time. Okay, and you have a maximum of 10% of the time two heteroplex DNA on two different chromatids. Those come from the resolution of double holiday junctions by structure-specific nucleases, different from the main pathway that generates interfering crossovers.
So I think, let me see. I think there is a question from Akshay. I think Bertrand, you can also probably see it in the chat box.
So is it possible to computationally identify certain regions that are more likely to have non-crossover or crossovers? Well, this is an excellent question, and this is exactly what we are trying to investigate now. So, what I presented you today is the analysis of only a few meiosis, but the interesting point of yeast is that there's I didn't mention that, but per meiosis there's almost 100 crossovers and 100 non-crossovers per meiosis. So studying only a few meiosis allow us to analyze hundreds of events and to have a quite clear view of what's going on in terms of events in a cell. But what we cannot do using this strategy is to exactly to know if a specific region is more likely to undergo a crossover or non-crossover. To circumvent this, what we are now doing is taking advantage of the evolution of the sequencing strategy. We have now generated sequencing data for several hundreds of meiosis. So now we will have some redundancy per loci. So we will know per loci if we have specific loci that are undergoing more frequently than other, either crossover or non-crossover. But that requires an even higher number of genomes analyzed, and higher number of genomes analyzed, more money, more time, more computational power, etc. But this is a very good question, and the answer is we should know that in the future, like in a year from now, we should have a clearer view of that.
Yeah. Anyone else?
Yes, sir. Nisha, yeah, it looks there is somebody raised the hand.
Oh, is it? Maybe the person can speak up. Yeah, I want able to see that.
Sir, I have a question.
Yeah.
Yeah. So, sir, as you have shown in your one slide, there is monochromatic vision in the so as you said, we resolve into non-crossover either through SDSS way or it will dissolve to non-crossovers. So I want to ask you that, do you have any idea how this type double crossovers formation happens? Basically, when double crossover formation happens, all 4 chromatids are involved in order to get the disease, right? So as you said in your slide that most of the non-crossovers are either through the agent of this single-stranded DNA or through the dissolution. So what suggestion crossover kind of is?
So Nishan, the connection was bad. So
Yeah. Even, I think Suman, you were asking about double crossovers, is it?
Yes, sir.
Can you just type it out? I think it was not clear.
Am I audible?
No, you can just type it out in the chat box in just 1 or 2 lines.
Okay.
Yeah, did you type it?
Professor Nishant.
Yeah. Okay.
Can we continue, and maybe we can answer in the chat box?
Yeah. I think we can.
Okay.
Yeah,
sure.
Okay, so Bertrand, thanks very much for the presentation. Yeah,
thanks
and
for your patience.
Yeah, and yeah, I look forward to meeting you also, okay, in the future, and hopefully can listen to you more. Yeah,
okay.
I think Suman will probably just email the question to you, and
Okay.
yeah, maybe you can just answer it. Yeah.
Okay.
Okay. Thank you. Yeah. Thanks.
Thanks again.
Bye.
Nagaya, can we begin with the next session?
Yes, sure.
Okay. Good evening. Welcome back for the final session of the day. We have two speakers with us for the final session. The first is Professor Heather Kulik. Let me first begin by thanking Professor Kulik for having accepted our invitation to deliver the talk. We are very pleased to have her with us today, this evening. Of course, it's morning in the US now. So without taking much time, let me briefly introduce Professor Kulik to the audience. Professor Heather Kulik is a computational material scientist at the MIT. She earned her bachelor's degree in chemical engineering in 2004. She then moved to the MIT for her graduate studies and worked under the supervision of Professor Nicola Marzari. She graduated in 2009 with a PhD in material science and engineering. She then pursued her postdoctoral research at the Lawrence Livermore National Laboratory, where she also worked alongside Professor Todd Martinez of Stanford University and Professor Judith Klinman of the University of California, Berkeley, on the large-scale electronic structure of biomolecules. Professor Kulik joined the faculty at the MIT in 2013. Her research group focuses research on the computational design of new materials and the use of artificial intelligence to predict material properties. Some of her favorite research topics include strategies to improve the accuracy of density functional theory, enzyme catalysis, transition metal chemistry, and atomistic simulations. Professor Kulik has numerous recognitions to her credit, some of which include the ACS OpenEye Outstanding Junior Faculty Award, Journal of Physical Chemistry and Physics Division Lectureship Award, National Science Foundation Career Award, and more recently, the Sloan Research Fellowship. With these words, may I now invite Professor Kulik to deliver her lecture. Professor Kulik, the floor is yours.
Thank you very much for the kind invitation and the wonderful introduction. So today I'm going to tell you a little bit about some of the work my group has done in thinking about how we can accelerate the design of catalysts and materials. And so in particular, our interest came from this challenge that while computation has gotten faster and faster, and computational chemistry, especially with DFT, that's the bread and butter of what my group does, has gotten more and more accurate, as you'll hear in the talk after mine. It's still not fast enough to address the really big challenges of understanding complex material spaces. And so we're interested in not just explaining the world around us, but also going out and discovering new materials. And in particular, when you have this kind of needle in a haystack challenge of trying to look out into transition metal complex space and solve a problem, maybe the optimal material that you want to work on or identify depends on the property that you're most interested in. So maybe the optimal material is this one or this one, and so on. And so we wanted to develop an understanding, sort of an atom by atom way of understanding what it takes to accelerate discovery in open shell transition metal chemistry. And so you could imagine, depending on the property, maybe it's the metal center that matters most. Maybe it's the direct coordinating environment of the metal center. Maybe it's the whole molecule. It really depends on the property. And so today, I'll tell you about some applications near and dear to my heart, especially as a chemical engineer and material scientist. And the reason that we focus on this material space is because it's both promising and challenging for applications. Some of the best catalysts are these well-defined metal centers with organic bits around, whether they're in single atom catalysts, homogeneous catalysts, or metal organic frameworks. These motifs also show up in energy storage, and I'll hopefully tell you an application in energy storage today. And then finally in designing scalable materials for things like gas separations and uptake. So a lot of the outstanding challenges we have in energy storage, utilization and resource utilization could be solved if we knew how to atom by atom on a computer design materials. This idea of having a language and a way of designing from the ground up is not new. A lot of what I described had been really pioneered maybe 20 years ago in organic chemistry. And there are lots of neat tools when we were first starting out, maybe about 7 years ago, that we wanted to just take off the shelf and use. These include things like SMILE strings that encode from a chemical connectivity to a 3D structure, low-cost methods such as force field models and semi-empirical models, large databases of multi-billion molecule fragments of organic molecules exist. These include things like Chembl or zinc. And so while it may not be the entire chemical universe, it's a pretty good start. And then concepts of molecular similarity of picking out the 10,000 most interesting compounds in the space. But what we quickly encountered was when we went to try to apply these tools for open shell transition metal chemistries, we ran into roadblocks at every turn. And in particular, things like SMILE string can't encode oxidation and spin state dependent structural changes. Density functional theory that I already mentioned once is pretty much the bottom rung for these types of materials. The types of databases we have access to are things like the Cambridge Structural Database, which I'll come back to, but these are materials that have been synthesized and studied experimentally, so they're not a great place for discovery. They're basically a place to tell us what people have already been fascinated with. And then concepts of molecular similarity that routinely work for organic chemistry can fail pretty easily for open shell transition metal chemistry. So we took a divide and conquer approach, keeping in mind that open shell transition metal complexes are in large part organic molecules with a metal center in the middle. And here's a fairly pedagogical motivation for why we did this. So if you think about the variation in bond length from triple bond to double bond to single bond, in an organic molecule, this follows a very natural expectation of ours of how bond order works. It's very linear. And as a result, force fields can do a really good job. Those are what the blue dots are at identifying how the bond length will change. In contrast, in inorganic transition metal complex, where all we do is change the spin state and the oxidation state and look at how the metal ligand bond length varies, it changes in a highly nonlinear fashion, even though the chemical structure, the Lewis diagram we would write down, hasn't changed. And as a result, force fields can only predict one of these points, and it's not even the one that the force field was aiming to predict. So when we first started out doing this, we used a force field for the organic bits in our divide and conquer approach and a DFT database for the remaining, the metal ligand bond length. And we developed code MolSimplify that enabled the automated command line structure generation of these transition metal complexes for high throughput screening. And we exploited things like where the organic parts worked, the concepts of similarity to search these multi-million molecule ligand libraries for candidate ligands to repurpose for transition metal complexes. And all of this is in MolSimplify, our open source code. I won't say too much more about MolSimplify except to say you can use a light front end of it after my talk. You can check out some of the advances that we've put into there with no installation, or you can install it via Conda or GitHub. And so the first thing we went out and did with this was we explored what I call transition metal complex neighborhoods. And simply by scaling up the size of material spaces, we explored from, say, the 10 to 20 that I might have studied happily as a PhD student to around 500 or so that we studied now with high throughput density functional theory and automated calculations. We were able to break our own expectations, defy conventional wisdom, and identify exceptions to standard heuristics. And so this included ways that suggested that, for instance, how to redesign quantum dot precursors for quantum dot synthesis, or how to make better catalysts for direct methane to methanol conversion. In all cases, we were able to defy what people thought was the right way to design these materials. But these calculations took quite a bit of time, so they would take us easily months to get 500 or so results. And you can very quickly realize that just doing high throughput DFT alone was not going to get us out to this transition metal chemical space that I mentioned on my first slide. So we knew that something faster than high throughput was needed to address all of the challenges with open shell transition metal chemistry, including the fact that metals can access multiple spin states, oxidation states. There are multiple metals we want to work with. And in particular, the diversity of the ligand structure in transition metal complexes is high. And so when we think about the trade-off that we always have to choose when building a machine learning model of how much data we have, how much model complexity we can tolerate, and what way do we want to represent our problem to a machine learning model, these optimal choices are always problem dependent. But in particular, trying to accelerate chemical discovery in open shell transition metal chemistry was hampered somewhat by the fact that we work with relatively diverse ligand structures, multiple metals and oxidation states and spin states, and relatively small data set sizes as a result. And so when we first got into this, this was a homework assignment of my first year graduate student, who has now since graduated, John Paul Genet, who's at AstraZeneca now. And he asked me, I have some machine learning homework to do. What would you like me to be able to predict? And obviously I was quite a skeptic. And so my first request was, I'd like you to predict the quantum mechanical ground state spin of these molecules and the spin splitting between the lowest energy state and the next state. I'd also like to predict how sensitive this result is to the exchange correlation functional. And then because we had this machinery that had a divide and conquer approach to building structures, I wanted us to not use any geometric information, but actually predict the metal ligand bond length. And the same approach we developed here went on to work in other properties such as redox potential, HOMO-LUMO gaps, reaction energies, and so on. And we use relatively modest data sets, only about a couple thousand complexes in size of mononuclear octahedral transition metal complexes. We addressed the DFT challenge by training on a family of functionals. I'll show you how we've since gone beyond that in more recent work. And we worked with metals in at least 2 spin states and oxidation states with common ligands. And where we really focused most of our effort was in thinking about how are we going to represent transition metal complexes to the machine learning models. So the status quo at the time was to think about representing all of the atoms and their identities to the model, but we knew heuristic theories like ligand field theory work really well by focusing only on the metal and direct coordinating environment. And so we imagined that the right answer must be something in between. And so we actually ended up doing this 2 ways. Once first for the homework assignment, and then we went back and did it shortly another way. I show both because both actually worked. So the first way we did this was we just did an ad hoc representation of just thinking about everything I knew mattered for open shell transition metal chemistry, things like the metal, the direct coordinating environment, things we had discovered during our DFT studies of differences in electronegativity and bond order and so on. And we even dug into the therapeutic drug discovery literature to something called the Keir truncated shape index to try to think about how does rigidity around the metal influence properties. And we retrospectively called this MCDL25. It's a fairly sparse descriptor set, but we weren't satisfied because there are other properties like the atomization energy that people were very interested in at the time that scale and depend strongly on the number of atoms in the system. And we might ask ourselves, well, how do we fill the gap here, and how do we develop a more systematic approach to go from these very local descriptors that we had developed to predict things like spin state versus other properties we know are going to depend more on the overall structure of the molecule. And so we went back and we developed something we call revised autocorrelation functions, or RACs. And they're, again, also geometry free. They're products and differences on the molecular graph. They're extensions of Moreau-Broda autocorrelations. They have an adjustable depth, so they don't depend on geometry, but they depend on the number of hops on the molecule. And the 5 properties we tend to work with are nuclear charge, electronegativity, covalent radius, topology, and identity. And all the RACs can map back onto these descriptors I've just shown that are ad hoc. For instance, the zero depth identity RAC is the number of atoms in the system. The zero depth ligand centered or metal centered Z-RAC are the metal and coordinating atom environments, and so on. And I'm going to show these descriptors several times again throughout this talk. And when I do, I make color nuclear charge and electronegativity blue for electronic character, and topology, identity, covalent radius yellow for geometric character. In all cases, these are just properties we look up from a table. So once we know the chemical structure of our molecule, it costs us nothing to compute this representation. And when we need information only close to the metal, we'll call these proximal descriptors. And when we need a lot of overall distant information, we'll call them distal. And so a principal component analysis of the first property we wanted to predict, which was the high spin, low spin quantum mechanical spin splitting, shows us why it's important to build a representation like we did with MCDL25 that was very local in nature. And in particular, an overall representation does a really good job of clustering these molecules by size. And so you can see this one example of a 150 atom complex versus a 37 atom complex, but they have very similar metal local environments. And as a result, the property we want to predict is really similar. So giving a machine learning model this information in this way will make it work really hard in order to understand and learn that these two molecules are very similar. Whereas in our local representation, the 2 points are quite close together in space. And so the model has to do a lot less work. As a result, our MCDL25 ANN could correctly predict 97% of DFT ground state spins. The cases where it was wrong tended to be the cases where the 2 spin states were near degenerate. And on the same exact data set size, our local representations had root mean squared errors of only a few kilocalories per mole, where the conventional approach would have had errors on the scale of 30 kilocalories per mole. And this is powerful. If you've never run a DFT calculation, doing the DFT calculations to get this property prediction would normally take us hours to days. And so if we trust this machine learning model, once trained, it can make a prediction in a second or so that would normally take us hours to days. And this allows us to start to think about chemical discovery. And we could actually do one better. So this is MCDL25. Again, MCDL25 was a series of ad hoc descriptors based on what I thought I knew about transition metal chemistry, whereas RAC 155 is the full RAC set. And you can see that we are getting down from about 2.5 kilocal per mole mean absolute error now down to 1 kilocal per mole, which is now getting us to the point where we're actually predicting really close to the DFT answer only in about a second. But you might think that this performance was good just because the feature set is bigger and it's overfitting. But when we apply feature selection, either on the property we want to predict, in this case spin splitting, or on a series of properties, which we call the overall universal URAC26, we do pretty much just about as well on a feature selected subset. And so the result is now we can actually get to within the DFT answer in about a second once we have sufficient training data. And these observations on spin splitting also apply to things like predicting the redox potential or the gas phase adiabatic ionization potential. It also applied to us being able now to supersede that force field I showed you on one of my first slides. Reducing errors for predicting the metal ligand bond length from an average of about 0.1 angstrom down to 0.01 angstrom. So now we can start a geometry optimization pretty much at the end, predicting overall structure before we even set up a geometry optimization. And if we look at what is different about MCDL25, you may be wondering what is different about a set of descriptors that I came up with ad hoc versus this RAC 155. You can see that MCDL25, as I mentioned, is highly proximal in nature. When we switch to RAC 155, just by nature of the expansion itself, it ends up being very distal in nature. That's just how the products and differences work out. And when we apply feature selection and obtain something like URAC 26, the one selected on a series of properties, we can see that it actually agrees really well with MCDL 25 in terms of how little distal information matters. But where the two differ are that URAC 26 weights more heavily mid-range features. And the reason we didn't come up with that with MCDL 25 is we just ran out of creative ideas for how to represent that mid-range information. So showing this another way, what we can do is better than just making good property predictions. We can think about from the racks, what are the most important selected features. The way we normally do this is we do random forest, pre-ordered recursive feature addition into a kernel ridge regression model. But regardless, we identify the most important features for making a prediction, and then we can analyze them to understand why the model's making the prediction it is. And so here is where I'm going to weight it. Blue if electronic heuristics matter more, yellow if geometric heuristics matter more. And this is an abstraction on a porphyrin here, but it represents our entire data set. I'm going to make the atoms big if they're important in the prediction. So if it's the close atoms or the far atoms, and I'm going to make them small if they're unimportant in the prediction. And so this is two different ways of looking at spin splitting with different cutoffs for how many features we include. And what both of them show you is that ligand field theory works. So they show you that what's going on at the metal is really important, and specifically the electronic environment around the metal is really important. Everything else further away matters a lot less. So that just tells us the model's making the right prediction for the right reason. We can then contrast this with things like geometry, predicting the metal ligand bond length. And this is interesting because it's a much more overall property, and it depends on both electronic and geometric factors. So we care about what's going on in the metal ligand bond, but we also care about how much steric bulk there is and how much through bond interaction there is that can influence the metal ligand bond length. And then if we look at redox potential, it lights up an entirely different part of the molecule. So now atoms far away from the metal matter most, and their geometric character matters most. And this gives us a map now, exactly what I proposed at the beginning of my talk, of telling us that atom by atom design of different properties requires knowledge and tuning of different atoms in our complexes. It also gives us a path to orthogonal design. So we can think about designing one part of the molecule to tune its redox potential and another part of the molecule to tune its spin state. And I'm going to show you this a few more times in this talk. So I want to show this as pie charts now. So it's a little less pretty, but it's easy to interpret. And the main thing to note is that when there's a lot of gray in the pie chart, it's a very non-local property. When there's a lot of blue in the pie chart, it's a very metal local. And each little wedge is the specific property of interest. So everything I've shown you to this point has been with one exchange correlation functional. It's been with B3-LIP, which is a GGA hybrid. And so you might be wondering, well, these are design principles and design maps. Do they just depend on the functional we use? Is this just a consequence of using density functional theory? And so what we did was we went back and we looked at a property like spin splitting, and we studied it with 23 different density functional approximations, ranging from pure GGAs all the way up to double hybrid functionals, which are quite computationally demanding. And we can see overall that most functionals, with the exception of a few bad actors like M062X, most of them actually agree really well. So they're all really correlated. Things with high spin splitting with one method are high spin splitting with another, and so on. So the Pearson's R for all of these is pretty good. And this is what it looks like. So something like TPSS, which we normally think of as a very accurate functional if you're a DFT practitioner, versus something like B-LIP, you can see that these correlations are in fact really good agreement among the data. And even when the agreement is really poor, like B-LIP with M062X, you can see that there is some overall structure still in the data. There are exceptions, but there's definitely structure, and there's definitely some correlation in the data. And so if we wanted to look at what it is, where do these methods agree versus disagree the most, it turns out that if we take the average of the percentile rank of all of these different materials for predicting spin splitting, and then we size the spheres by the standard deviation in the property. This is visualizing in the latent space of one of our machine learning models that we went and trained on this data. What we see is that the midpoints, so the points close to near degenerate spin states, are the ones where the methods actually disagree the most. And so that's a bit concerning, because those types of materials are really attractive for designing switchable materials that can change their spin states and in response to stimuli. But it gives us a path to understanding that in the extreme cases, all the functionals will generally agree. But if we then require consensus, we say, well, let's pick all of the spin crossover materials. Those are near degenerate spin states with spin splitting around 5 kilocals per mole. And we ask, if we require most of the semi-local functionals to agree on what makes a spin crossover material versus most of the hybrids versus the double hybrids, do these different functional classes then agree, different rungs of Jacob's ladder? And there what we find is that, in fact, there's very limited agreement between semi-local functionals and hybrid functionals. There's a little bit better agreement between hybrid and double hybrid. But in general, if we require this type of consensus across different families of functionals for spin crossover, we're going to get a very small set. Now, this is property dependent, because if we then instead use the delta SCF method to obtain the HOMO-LUMO gaps of materials, which is a fairly good way to reduce some of the functional sensitivity of the HOMO-LUMO gap, then we actually get considerably better overlap between these different 3 families of functionals in terms of identifying what gives rise to a HOMO-LUMO gap. So the difference here between the correlation plot and these Venn diagrams is that in the correlation plot, we're just requiring what's high be high, what's low be low, whereas here we're focusing on targeting a specific property value, and you can see the functionals disagree much more about property values. So what is robust? What is invariant? And I mentioned to you that the pie charts are our friends, right? So the pie charts give us a new way to understand what it takes to engineer and design a property. And this here, I'm showing the BLIP pie chart for spin splitting. And here is a pie chart for the delta SCF gap, or the vertical IP. This shows 2 quantities very similar to the redox potential I showed you a few slides back. And what they both show us are that properties like the HOMO-LUMO gap and the vertical ionization potential are much more non-local in nature. But this is the picture of the world with BLIP. So we might ask ourselves, if we change the functional, are we going to change these pie charts? And the good news, the really powerful news, is no. So we could change to a more highly parameterized M06L functional, which is a pure meta-GGA. We could change to M062X, which I pointed out correlated pretty poorly with other functionals. And we can even go and do the heroic effort of doing a double hybrid, such as the PB0 double hybrid. And what we see is that for the most part, the key features of the pie charts differ significantly more between properties. So we see that consistently spin splitting is the most metalocal in nature, with a very small amount of global features that matter. Whereas vertical IP is the most non-local in nature. We can see that these pie charts are relatively invariant to the functional on which they were trained. And so this gives us a new way of thinking about making property predictions. We can obtain these pie charts on a low-cost functional with a small basis set. And we can then use these design principles to guide selective calculations with higher levels of theory. So having overcome that source of uncertainty, we got to think about how we're going to actually use our machine learning models, in this case, artificial neural networks, to carry out chemical discovery. And there's 2 ways you can think about doing this. I'm going to show you both of them. So one way we can do this is we can exploit where we can trust the neural network. And so we can start with a discrete candidate pool, and we can use something we call uncertainty quantification to then combine with an optimization algorithm to say, let's find the best molecules in this candidate pool where our neural net can be trusted. And for the optimization algorithm we're going to use for this, it's going to be a genetic algorithm. There's nothing special about genetic algorithms. We take the metal and ligand identities, treat them as genes. We evaluate their fitness. In this case, what's special is we use the neural net to evaluate the fitness, so it's much faster to accomplish this. Then we carry out steps like crossover and mutation to keep up diversity. And then we finally end up with a set of best materials. What we do that's special here to the neural net is we need to know where the neural net can be trusted. If we go too far away from anything the neural net has seen before, it may be untrustworthy. And so for uncertainty quantification, we carried this out two ways. In one case, we use what we call the feature space distance. So how distant are compounds in the feature space? So the features I showed you earlier, or we can use the last layer of the neural net, which is called the latent space. That's how the model perceives the proximity of different materials. And this is important because even though we can get low test set errors around a couple kilocalories per mole I mentioned, if we go to totally new spaces, those errors can rapidly rise because the neural net doesn't know anything about the totally new materials. And so if we constrain ourselves to only making predictions where the new data is well supported by the prior data, either in the feature space or the latent space, and we don't make predictions where the new data is too far away, then we can rapidly crank down and be more conservative and crank down the errors on the new predictions we make. And the way we incorporate this into a genetic algorithm is simply by using a composite fitness function that penalizes high distance points. And as a result of doing this, we can basically expand rapidly our space of materials that we study. Here we're looking at 10 to 30,000 catalysts and materials, and we can explore all of them and rapidly identify new materials at roughly the same quality as with DFT calculations. And we can do this for spin crossover complexes, for designing HOMO-LUMO gaps, or for discovering unexpected methane to methanol catalysts. So we can also do this a different way. I mentioned that different DFT functionals, especially from different families of density functional approximations, might give different absolute property predictions. So that's another source of uncertainty. And so what we did was we used 23 DFA trained neural networks and required at least half of them to agree on what makes a spin crossover complex in a space of 182,000 candidate materials. And here what I'm showing is the convex hull of those consensus materials in blue in comparison to what is an experimentally characterized spin crossover complex versus what we would predict with a single DFA. And so you could see that the consensus approach gives much better agreement with predicting what is an experimentally validated spin crossover complex. And it allows us to suggest new combinations, in particular that cobalt with nitrogen is a relatively underexplored material for spin crossover complexes. And these are more robust predictions because they don't have the bias of just a single density functional approximation. But those are ways we can exploit the models where the models are well trained. In practice, in real life, we often need to go out and explore new material spaces where we have limited prior training data. And one way we approached this was in thinking about doing redox flow battery, redox couple design. And in trying to design redox couples for non-aqueous polar electrolytes and redox flow batteries, some of the things we need to think about are maximizing the redox potential, maximizing solubility, and avoiding crossover. And so typically one of the oldest materials in these types of systems has been vanadium ACAC complexes, but we're interested in exploring new materials with new metals that had been relatively underexplored for redox flow batteries. And so, as I mentioned, this is really a multifaceted challenge now. It's not just one property, but we want to address the challenge of stability and resistance to crossover. We also want to maximize solubility, and we want to maximize the redox potential. And the way that we address stability and resistance to crossover was thinking about designing our candidate material pool from the ground up. And so we started with synthetically accessible heterocycles, so things that commonly appear in experimentally synthesized materials. We fused them together. We added functional groups that can be expected to tune the solubility and redox potential, and we combine them with 4 metals, chromium, manganese, iron, and cobalt, that have been relatively underexplored for these types of applications. And as a result of just the combinatorics of the spaces, we end up with 2.8 million bulky homolectic transition metal complexes that look nothing like anything my group had studied before. So many of these have 100 to a couple hundred atoms in size. Just doing one DFT calculation accelerated on GPUs takes around a week. And so these are calculations that are really slow and challenging, and for which we had no prior experience. And we're going to do something we call active learning now, and we're going to use multi-objective optimization. I'm going to show this once in a cartoon form, and then I'm going to show it again with what the real data looks like. And so we're going to use, again, an uncertainty quantification and an optimization algorithm here, but to do model exploration rather than exploitation. And so we'll put our 2 objectives, our maximizing solubility, we'll use log P as a proxy for that, and redox potential will be the other thing on our axis. We'll go out and we'll set up 64 GPUs to run full throttle and generate as much DFT data as we can. This is a cartoon, but it doesn't look too different from how much we're able to generate in about a week's time. Then we're going to take those handful of points and train a neural network and ask the neural network, what do you think about these 2.8 million candidate materials? And what our goal is to move forward the Pareto front. So we're looking for things in the bottom right-hand corner of this plot that have the optimal trade-off of solubility and redox potential. And so we're going to use something called the expected improvement algorithm to identify both uncertain and promising points past the Pareto front that can maximally enrich our ANN. We're going to score them. We're going to come up with candidates. We're going to go back to DFT, ask DFT, what do you think about these candidate materials? Then we're going to see that not all of those predictions by the ANN were correct, but we can now ingest all of that data into retraining the neural network and starting again. And so this is what this looks like. So running 64 GPUs full throttle on my cluster in about 2 weeks' time, this is all the data we get. And so these are the data in property space, and the different shape of the symbol is if it's a chromium material, manganese, iron, or cobalt. And so we go to the neural network, and in about 3 minutes, we can ask the neural network, what do you think about the 2.8 million compound space using the information from those DFT calculations? Here, we've scored the space by the expected improvement score, and the blue shows the actual Pareto front of the previously characterized compounds. And so you can see the expected improvement score is highest for points that have the greatest promise for going past this front. So we take some of them and we go back to DFT, and after about a week's time, you can see that only some of them actually move the Pareto front forward. The neural network wasn't very smart about the space yet. But we can go and we can retrain the neural network, and in another few minutes, we can ask it, well, which new points should we pick out now? And you can see this time the neural network was quite a bit smarter. So after about another week with DFT, this is how many new points we get. We repeat this again, and you can see that we're getting more and more pessimistic. The expected improvement score is getting less and less lit up. So there are fewer and fewer points that the neural network believes can go beyond the Pareto front. This is another week with DFT. And after another few minutes with the neural network, in total, we spend 6 weeks with DFT and about 15 minutes with the neural network. And we end up with a Pareto front that's largely only points from the last 3 generations of our ANN. And we decide we're at basically diminishing returns, and so we stop the process. And we obtain convergent design principles. So basically everything sitting on this Pareto front, especially if high redox potential is our priority, we observe that manganese high spin complexes with sulfur in the ring and oxygen coordinating the metal are important. We also need small polar groups to increase solubility without reducing the redox potential. That's something that I could have told you from that pie chart and porphyrin I showed you at the beginning of my talk. If we really care about solubility, we might instead pick out bigger, bulkier groups, but we'll do that at the cost of sacrificing redox potential. so we can ask ourselves, how much faster did we obtain this result? Which we obtained still with 64 GPUs running full throttle. We got those results in about 6 weeks. And we can do a conservative estimate. A conservative estimate tells us that we got at least 500-fold acceleration. And the first time I heard this, I thought, oh, that's terrible. Anyone can do something 500 times faster. And then you realize that it's 500 times faster than 6 weeks. And so if you multiply 6 weeks by 500, you get 5 decades. And so you can realize that this means the difference between having an answer in a month's time versus not having one in our lifetimes. And now that we've demonstrated this on redox flow batteries, we're now demonstrating this in my group on multi-objective catalyst design, earth abundant materials design, and so on. But I'd just like to finish with a brief story about metal organic frameworks and to say, how are we starting to extend this to scalable materials like metal organic frameworks that are really well studied. And so typically what people do when they focus on gas separation with metal organic frameworks is they focus only on the geometric nature of the MOF. So we asked ourselves, could we use and extend racks to metal organic frameworks, thinking about breaking apart a MOF into its substituents like the metal inorganic SBU, the functional groups, and the linker chemistry, and so on. Indeed, what we find is that adding racks improves the models, but more importantly, we can use the selected racks to guide and inform us when chemistry matters the most. And so if we think about methane uptake in low pressure versus CO2, CO2 is a much more electronically interesting molecule. And so as a result, we get a lot more features that depend, the red, purple, and green depend on the chemistry of the materials, whereas blue is the geometry only. And so you can see that CO2 depends strongly on the chemistry. And this chemistry dependence goes away if we go to really high pressures, then geometry takes over. And this makes sense because at really high pressures, we're just shoving molecules in there, and all that matters is how much space is available to us. But it turns out these conclusions depend on where we get the data from when we use this in the ML models, if we get it from so-called hypothetical sets of MOFs versus if we get them from synthesized materials. So again, projecting now in rack space, either based on the metal geometry, the metal chemistry, the functional group racks, or the linker racks, or pore geometry, what we observe is that when we see gray points, this means that's only in the experimental data sets, versus if we see colored points, that means it's present in the hypothetical data sets. And the reason that metal chemistry importance is sensitive to the data set is because these hypothetical data sets actually have very poor coverage of possible metal SBUs. So what we did was we went back to this experimental data set. It's called the Core MOF data set. And what it is it consists of all experimentally characterized MOFs in the Cambridge Structural Database that have been cleaned up and are ready for computation. And so hypothetical sets should really mimic have the same diversity as this set in order for us to make predictions. And that's something to think about in materials. But we can leverage this data set because it has about 10,000 MOFs that are featureizable. And we can featureize all of them with racks. We can then work with all of them to identify experimentally extractable quantities, such as thermal stability and whether or not they're stable with respect to removal of solvent, which we call activation. And so it turns out we can use machine learning models to actually predict these quantities based on the experimental result alone. And this is important because doing the simulation to predict these quantities would be really hard. It would be really hard to predict when a material is going to fall apart when we heat it, or if it would be stable with respect to solvent removal. And we can also build a model for predicting the temperature at which these degrade. Overall, what we can see is that these two properties are pretty closely related, but they depend really sensitively on the linker chemistry. And so this allows us to identify ways that we could engineer new materials or predict the thermal stability and solvent removal stability of these materials. In total, we could make predictions with our ML models once trained on 1,500 unseen materials for which the ML model is confident, orders of magnitude faster than the best alternatives. So I think I'm just about out of time. So I'd like to conclude by saying we started all of this thinking about how do we do high throughput open shell transition metal chemistry. This led us to the first machine learning models to predict open shell transition metal complex properties, which our ultimate goal was to both accelerate the discovery of new materials and come up with new ways to reveal design principles. Everything I mentioned is available on Conda and GitHub, but you can also play with our neural net on our website. And do some of the simple structure generation. And I'd just like to conclude by acknowledging the students who did the work. I had the pleasure of telling you about work first pioneered in my group by John Paul Janae and Tim Ioannidis, as well as a recent work by Aditya Nandi and Chen Rudwan. And thank you very much. And I'll take any questions if there's time.
Thank you, Professor Kulik, for that wonderful exposition into the ML models as applied to chemistry. The floor is open for discussion now. Are there any questions? Okay, perhaps I shall begin. So in the descriptor space that you talked about, was there these polarizabilities that have been taken into account? I mean, I probably missed it. You had a list of the parameters that were taken into the model, right?
Yeah, so we normally don't use atomic polarizabilities in the in a lot of our early models. We use nuclear charge, electronegativity, covalent radius, topology, and identity. But actually, when we do some of this MOF work, the MOF community has been big fan of atom-wise polarizabilities, and so we actually do use atomic polarizabilities here. But because in all cases we're essentially encoding trends from the periodic table, you sort of get at the atomic polarizability by a combination of nuclear charge and covalent radius as well. So we're mainly trying to encode differences in quantities in the periodic table. But that's a good point, is that feature is something that had been motivated in the past, and we are actually using it here.
Okay, thank you. Does anyone else have a question? I did come across your recent article which says, are we computational chemists out of business because of this ML models? I just wanted to know if you have any comments regarding that.
Yeah, so I consider myself first and foremost a computational chemist, and I think that ML has definitely changed how a lot of us are doing science, and it requires some adaptation. I also think a lot of this is automation, right? So thinking about if we no longer have to do things by hand, what are we freed up to do? And I think that's something that's coming to a lot of fields. Yeah.
Thank you. So is there any other question? No? Okay, so let's join in thanking Professor Kulik for a wonderful lecture. Professor Martin, are you there? Professor Martin?
Hello.
Hi, good morning.
Good morning. I apologize.
Welcome to the HPC workshop.
Thank you. My computer decided to update its software for the last 15 minutes, which is unfortunate. I apologize for being a little late.
We were anyway running behind schedule by 10 minutes. So you're on time.
Okay, well, that's fortunate. Okay, well, I guess I can share my, well, let's see. So when I'm ready, I can share my screen.
Sure, I'll take a couple of minutes to introduce you to the audience.
Well, that sounds good.
Madam, what is the ID? Because I could not find. To
Which
make him
ID?
as a co-host.
Co-host,
So
MHG.
Okay, I will do that.
Okay. So welcome back for the final talk of the day. We have Professor Martin Hedgorden with us. Very pleased to have him with us today, this evening. Professor Hedgorden is a computational quantum chemist at the University of California, Berkeley and Lawrence Berkeley National Laboratory. He received his Bachelor of Science and Master of Science degrees from Monash University in 1985. He then moved on to the Carnegie Mellon University to work with Professor John Popel for his PhD. Subsequent to his graduation with a PhD degree in 1989, he pursued his postdoctoral studies at the Bell Laboratories during 1989 to 92. He is currently the Kenneth Pitzer Distinguished Professor of Chemistry at the University of California, Berkeley. Professor Hedgorden's research focus is on attacking the frontiers of electronic structure calculations by the development of novel theories and algorithms. His research combines fundamental quantum mechanics and many-body theory with aspects of applied mathematics and numerical analysis, as well as high-performance computing. He's very well known as one of the founders of QChem, the popular program that has been used extensively by quantum chemists. Professor Hedgorden is honored with numerous recognitions, some of which include the National Science Foundation Young Investigator, Medal of the International Academy of Quantum Molecular Sciences. He's also a member of the National Academy of Sciences. We are pleased to invite Professor Hedgorden for this meeting. And of course, his empirical dispersion corrections are what most of us quantum chemists use every day. So he actually doesn't need any introduction, but then for the sake of students, for the benefit of students, we do this. So the floor is yours, Professor Martin.
Thank you. Okay, so I'll share my screen. Let's see if we can get the technology to cooperate here. Okay, hopefully you can see a title slide. Anyway, so thank you very much for the invitation to join this exciting meeting in Kerala. I'm pleased to join virtually. It's early in the morning here in California, and I'll tell you something about recent developments in density functional theory, some on methodology, some on interpretation. And so my talk will be divided into three sections: a brief introduction to DFT for those of you who are not familiar with it, a section on designing and testing new density functionals, and thirdly, a section on trying to gain chemical insight from density functional theory calculations. Okay, today density functional theory is used around the world by on the order of 100,000 chemists, physicists, condensed matter scientists, material scientists. We are kind of grouped into camps, each camp developing a software package, a sort of an infrastructure that requires typically on the order of 100 or more people to cooperate together to build. Our code QChem that Swathi just mentioned is about 25 years old, contains more than 10 million lines of code, and has around 300 contributors, including quite a number who are based in India, I might add. The uses span all of chemistry. One that is of particular interest to me is the CO2 reduction reaction, modeling the currently not yet fully solved problem of how to catalyze artificial photosynthesis, driving CO2 from the bottom of the thermodynamic well up towards more useful molecules like CO or methane, methanol. And one can unravel relatively complex reaction pathways. This is an example from a cooperation between my group and the groups of Chris Chang and Jeff Long at Berkeley on a homogeneous CO2 reduction reaction catalyst. And DFT is arguably the dominant paradigm today in quantum chemistry because the trade-off between accuracy of the results and feasibility of the calculations is pretty good. And perhaps at a basic level, more or less 95% or so of chemistry is easy in the sense that density functional theory, a relatively simple approach to electronic structure, usually works pretty well. Of course, progress to this point is very much enabled by developments in supercomputing. And as this group is very well aware, without the instrumentation to perform advanced calculations, advances in algorithms mean nothing. So there's really a critical synergism between improvements in supercomputing and the ability to think about, to design new algorithms that wouldn't have even been relevant on earlier generation computers. And it's quite interesting to think that while we are approaching the exaflop era for the world's #1 fastest supercomputer, we're very much in the teraflop era at the node level, and a single node, 128 cores or so, delivers around 4 teraflops per second. That is 10 to the 4 times 10 to the 12th floating, adds and multiplies per second. And that's faster than the fastest supercomputer in the year 2000. So in a way, research in advanced scientific computing is very much democratized across the world these days because of advances in computing hardware at the low end, the medium end, and finally the high end. Okay, well, what is density functional theory, and why is it so amenable to computing? Well, instead of an exponentially complicated object, the wave function, so if you discretize a single coordinate x into, say, 100 grid points, then the coordinates of n electrons would require 100 to the power 3 to the power n grid points. In other words, 100 to the power 3n, or an exponentially growing number of grid points. Instead of that, density functional theory focuses just on the electron density, a function of only 3 coordinates, Cartesian x, y, and z. And so essentially there is enormous computational efficiency to this compact representation of the fundamental variable on which the energy depends. Beautiful Hohenberg-Kohn theorems guarantee that the ground state energy can be exactly expressed as a functional of just the electron density. Today, that theorem is best implemented by what is called Kohn-Sham density functional theory, where we use molecular orbitals to represent the density and the kinetic energy. And so the energy is divided into these 4 terms, 3 of which, kinetic energy, electron nuclear attraction, and classical Coulomb repulsion, are exactly known. And the one in red, EXC, must be modeled. And that is the task of the developers of density functionals, is to model EXC. The true exchange correlation functional is in practice, I believe, unknowable. So the theorems are a source of comfort for the developers of approximate exchange correlation functionals, but you cannot really hope to develop the exact density functional. Even if you could develop it, you probably don't want it because it would be too expensive. So really useful approximations to EXC balance accuracy against feasibility. And to kind of summarize the taxonomy of existing density functionals in a short talk like this is difficult, but the task is made easier by the great density functional developer John Purdue, who suggested that density functionals should be grouped according to a simple taxonomy, rungs on a metaphorical ladder climbing from the flat earth of the Hartree world toward the heaven of chemical accuracy in a series of physically distinct steps. The first step being to exactly solve the important model problem of the uniform electron gas, in which case the unknown EXC just depends on the density at a given point. To advance beyond that, we go to what are called the generalized gradient approximations, where the exchange correlation energy density at a given point depends not just on the density, but on its gradient as well, the spatial gradient. And I'll show you comparative results for methods at all of these rungs in a little bit. Climbing beyond the density gradient, you would naturally imagine that second derivative information must enter. And this is most popularly done through what are called the meta-GGAs these days, where the second derivative information comes in through the kinetic energy density, the quantity that if you integrate it over all space yields the kinetic energy multiplied by a constant. At rung 4, perhaps the most interesting rung for chemistry, we begin to leave the domain of local functionals to include non-local information. And the non-local information at rung 4 is in the form of exact exchange, the exact exchange associated with the cone-sham orbitals. This can also be viewed as a hybrid between true density functional theory and wave function theory, a little bit the way hybrid plants, borrowing the rootstock from one species to blend with the leaf stock of another species is so successful in agriculture. This is a blend between simple wave function theory using the cone-sham wave function and density functional theory. And that hybrid idea can be doubled at rung 5 with the so-called double hybrids, where not only exchange, but correlation also becomes non-local. And that comes in typically through either second order perturbation theory or maybe the random phase approximation. So this is a very quick look at the taxonomy of density functionals. It's only one way of looking at it, though. The other important way to look at it is, what do you get? And here is on the right-hand side of this slide is a look at the RMS errors for simple thermochemistry as you climb from rung 1 to rung 2 to rung 3 to rung 4, using a variety of popular functionals. Well, the LDA is fit with what is called the SVWN parameterization. BLIP is a popular GGA, MO6-L is a widely used meta-GGA, and MO6-2X is a widely used hybrid functional. And you can see a systematic improvement in the RMS error on this test data. I should also say that taxonomies are not always perfect, and the Purdue taxonomy of Jacob's ladder leaves out one factor that is so important that it must be mentioned separately, and that is non-local dispersion. The dispersion energy is kind of the uniform attractive background that leads to colloidal behavior, to self-assembly, to many, many other aspects of chemistry. And dispersion is not a function of the position of one electron. If I have, for instance, one body at position R1 in space and a second body at position R2 in space, the dispersion attraction depends on the relative position of R1 and R2, not the absolute position of any given electron. So to address this physical factor that's left out of standard functionals, it's now common for these functionals to be dispersion corrected. And that was in fact the correction that Swathi was referring to in the introduction. The damped C6 over R to the 6th potentials, which are really molecular mechanics potentials, or perhaps more popularly today, non-local van der Waals functionals like VV10 or VDW-DF2. And these corrections make a profound difference to the accuracy you can get with thermochemistry. So here is the error for two different data sets in lighter blue and darker blue for the popular B3-LIP functional without a dispersion correction. And here are the same errors on the same scale with a dispersion correction. And you can see the dramatic improvement, a factor of 4 to 5 reduction in RMS error by including the dispersion correction. Clearly an important physical effect. Okay, so to finish my introduction, if you have not already read this widely cited paper in Science, let me quote from it about the question of how we develop density functionals. And these authors say that density functional theory is straying from the path towards the exact functional, and the evidence they cite for that is that atomic densities became closer to exact ones, reflecting theoretical advances, until the early 2000s, when this trend trend was reversed by unconstrained functionals sacrificing physical rigor for the flexibility of empirical fitting. And I note that it may or may not be a coincidence that my group began designing density functionals in the early 2000s. Anyways, the data that was presented to support this is a bit funny, but take a glance. On the y-axis is the maximum RMS error in the atomic densities of 12 spherical atoms, and on the x-axis is the year in which a particular functional was introduced. And a dot on this plot is then a functional. And the line here is to sort of guide the eye, showing RMS error declining until shortly after the year 2000, when the errors began to rise again. And so that's what they were talking about. I would note that actually all 14 of the worst post-2000 density functionals were in fact developed by a single research group. So in a way, the statistics are a little bit biased here. If you removed those red points, in fact, it would appear that densities have been becoming more accurate even up to the present day. But there's a more serious point to be made, and I should also add that that group was not mine, but I won't tell you whose it was. Overall, the researchers conclude that DFT is in need of new strategies for functional development. And so my group has introduced one such new strategy, and that's what I'll tell you about next. We call this approach survival of the most transferable, and it's an assisted learning approach, essentially based on the idea of best subset selection. And this work was done by a brilliant student in my group, Nabe Marderosian. Nabe and I worked together for about 7 years on this project, and I'll tell you, where we got to. Okay, so the general idea of this survival of the most transferable is to use a combination of exact conditions to constrain the form of density functionals and empirical data. And the empirical data is then used to train a very large number of candidate density functionals. And in fact, Nabe and I have trained over 1 trillion density functionals altogether. With that many candidate functionals, we then have to down select and test and transfer. And this is the idea of assisted learning. So we use about 5,000 pieces of benchmark data split into roughly 20% training data, a bunch of primary test data that is used for the best subset selection to pick out the most promising functionals that were trained on just the 870 data points. How well do they transfer? Well, that's the best subset selection. And of course, the best subset selection is biased by the data that you use to select the subset. So finally, we save some data to as secondary test data to examine. The most arbitrary thing about this is the weights of individual test sets, which are set by humans, namely Nabe and I, and reflect what we think we are trying to get right and what we are willing to live with as not being perfect. And then finally, in terms of asking about parameters, what we were heading towards really, and we in some sense achieved it, is to be able to assess a large number of candidate density functionals as an XY plot, where on the x-axis are the number of parameters retained, and on the y-axis is the overall performance. And we should expect that eventually too many parameters will lead to overfitting. And so this kind of curve should flatten out and maybe even develop a minimum. And we only allow the inclusion of additional parameters if it has predictive power. This is not really meant to be read, it's just shown to show you that we categorize data into a bunch of groups, non-covalent interactions, that's the dispersion sensitive stuff. We further categorize non-covalent interactions into easy and difficult, E and D. Then the next main category is isomerization energies, then thermochemistry, then barrier heights. And so these categories will show up in a few minutes when I present some data. Well, a general talk shouldn't have too many equations in it, but if you're designing density functionals, you simply must have an equation that shows what the functional is. So this is what goes into the functionals we've designed. We use Becky 97 type forms for the semi-local DFT exchange, opposite spin correlation, COS and same spin correlation CSS. And then we correct this basic semi-local form, which can either be GGA, which is shown in blue here, where the GGA form is essentially an inhomogeneity correction factor to the rung1 functional, the LSDA, and these C's here are the parameters, and U to the power J, well, this is where the density gradient comes in dimensionless units. Then this semi-local form is corrected with a van der Waal density functional, VV10, and non-local exchange, which we do via range separation. So these, so then where does the functional search come from? It comes from the fact that we truncate these little polynomial expansions at finite order. Say there are 5 terms included in each of 3 expansions, meaning 15 possible parameters. Each of those parameters could be included on the one hand or excluded on the other hand. So there are then 2 to the 15th possible functionals that we could design from this space of functionals. And that is on the order of 100,000. We can search them explicitly. And so that's what we did at the GGA level. Okay, that's what I just said. If we go to the meta GGA level, a Taylor expansion in 1 degree of freedom generalizes into a Taylor expansion in 2 degrees of freedom, U and W. W now depends on the kinetic energy density in dimensionless units. And if you take a Taylor expansion with 5 terms in each of W and U, you then get 25 here, 25 possible parameters for the first component of the semi-local functional, times 3 gives you 75. So there would then be 2 to the 75th. 2 to the 75th is about 10 to the 23rd. That's roughly Avogadro's number of possible functionals defined based on the inclusion or exclusion of each possible parameter systematically. This is like a functional genome to search. Okay, so this is what we do search, and we try and work close to the complete basis set limit. This turns out to be important. We fix the nonlinear parameters that characterize range separated exact exchange and VV10 dispersion, and then we analyze systematic inclusion and exclusion of linear parameters in that kind of Y versus X plot of number of parameters on the X-axis versus performance on the Y-axis. And in this way, we've combinatorially designed 4 new functionals that inhabit rungs 3, 4, and 5 of Jacob's ladder. In this search, functional search, we are careful to try and exclude candidate functionals that will be inconvenient or uncomfortable to use in simulations. For instance, the functional must be easy to numerically integrate, so we exclude functionals that are not. The functional must be physical, so we exclude functionals that are unphysical in the sense of producing, for instance, exchange inhomogeneity correction factors that are negative. And finally, we want balanced errors. So as part of the assisted learning procedure, we exclude functionals that exhibit above average errors in any given category of chemical energy differences like thermochemistry, TC, or non-covalent energies, NC. And this is the kind of data we get. If I was to show you data for smaller than 10 parameters, you should imagine the errors being much higher than 5 kilocalories per mole. If I was to show you functionals with more than 16 parameters, it's basically flat and turning up. And if I pick a particular number of parameters, like say 15, you see a very dense collection of data points. So there is one functional that is best right down the bottom with an RMSD of 4.8 kilocalorie per mole. And if you were to just slightly loosen your standards and accept up to 4.85 kilocalories per mole, the prediction power of probably several dozen other functionals would be roughly similar. So survival of the most transferable actually produces many functionals of nearly similar performance. How do we choose one? Well, ultimately, it's a little arbitrary. This particular graph is from the search for an optimal meta GGA. And so to make the selection, we actually look for the first time that we get a good functional, something that approaches the best that can be had with any number of parameters. But in fact, we get that predictive power with 12 parameters, significantly better than we think 11 parameters, much better than 10. And so it's a slightly arbitrary choice. You shouldn't think of the result as being a distinctively good functional compared to other candidates we could have chosen. It's really a representative of the most transferable. But because most other functionals that are semi-empirical in DFT were never selected based on their predictive power, they were simply trained on as much good data as possible, the kind of performance we get with these selected functionals, selected for predictive power, is actually very, very significantly improved, as you'll see. All right, so I'm not going to belabor this, but there are 4 functionals. Rung 3, a functional we call B97M-RV, 2 rung 4 functionals, a hybrid GGA omega B97X-V, and a hybrid meta GGA omega B97M-V, and then a rung 5 functional omega B97M parenthesis 2. And their characteristics are quickly summarized here. Non-local exchange is range separated in everything at rung 4 and rung 5. Non-local correlation is VV10 type for dispersion, and then PT2 type at rung 5. The rank of the search space, well, it's even bigger than Avogadro's number, the way we implement it at the meta GGA level and the hybrid meta GGA level. It's only about 100,000 at the hybrid GGA level. And eventually we finish up with 12 parameter functional. That was the data I showed you. 10 parameter functional, 12, 14 parameter. So that's what we made. How do they do? Well, this is assessments on our data. And this is the 5,000 data points, non-covalent in C, isomerization energies I, thermochemistry TC, barrier heights 8 BH, easy and difficult E and D, and this NCED is dimers versus clusters. So non-covalent easy dimers, non-covalent easy clusters. In this assessment that's summarized in this 2017 review, we actually looked at over 200 density functionals on all this data, picking out the top performing functional from each rung. And of course, at rung 1, there's really only a single functional, that's the LDA, and you can see RMS errors of 10 for easy thermochemistry and 15 for barrier heights and 2 for easy non-covalent interactions, as such that this is nearly useless for chemistry. However, climbing to rung 2, we get things that are very substantially improved, and a reduction of roughly a factor of 3 to 4 in RMS error, and this is the B97D3 functional. We can't do better than that with our combinatorial approach because there are only 100,000 possibilities to search, and B97D3 is really about as good as you can do on our data. At rung 3, the new functional B97M-RV produces significant improvements. Easy thermochemistry is improved very significantly. Barrier heights by more than a factor of 2, non-covalent interactions by more than a factor of 2. Isomerization energies, easy ones more than a factor of 3, but nothing gets worse, everything gets better. At rung 4, the hybrid density functionals, our hybrid meta GGA serves up another factor of 2 for barrier heights, reduction in RMS error, a slight but significant improvement, it's statistically significant, the improvement in easy thermochemistry, and nothing gets worse, everything gets better. A big improvement for isomerization energies, small improvements for non-covalent interactions overall. And then finally, at rung 5, there is a further significant improvement in easy thermochemistry and barrier heights. So you can see that that in a statistical sense, density functional theory can be systematically improved by climbing Jacob's ladder if dispersion interactions are included. And you note they are included in the best functionals at rungs 2, 3, 4, and 5. This is our data, of course. If we go looking at someone else's data, this is another very large data set recently developed in Stefan Grimmer's group in Germany, the GMTKN 55 data set. And the functionals in green are the ones that I told you about. There is our meta GGA, the best performer at rung 3 on the Grimmer data set. Here is the hybrid GGA, the second best performer at rung 4, and the hybrid meta GGA, the best performer at rung 4, and at rung 5, and the overall best performer is omega B97M parenthesis 2. Of course, compute costs increase as you climb Jacob's ladder, so the most expensive functionals are the rung 5 ones. Those scale with the 5th power of molecular size and compute cost, compared to roughly the cube with a high prefactor at rung 4 and the cube with a smaller prefactor at rung 3 and rung 2. So that is roughly a summary of this. I just want to point out that there are some requirements to getting good numbers out of the new functionals, and that is that you need to use large basis sets. So here I'm showing you the convergence of results for easy thermochemistry as a function of basis set size with the PBE functional, showing you that there is not an enormous difference between a double zeta basis and a triple zeta, and essentially no difference between a triple zeta and a quadruple zeta. So a small basis is more or less okay for a GGA, but for a hybrid functional like B3-lip, you can see that there is a very large reduction in RMS error. It's about the same reduction here, but now it's, instead of reducing the error by 1/3, it's reducing the error by almost 1/2. And it's very much the same thing for omega B97M-V, where to get that good performance, you must use at least a large triple zeta basis. Anyway, so sometimes you do have to pay something to get something. Okay, so to summarize this part of the talk, we have introduced a new paradigm for density functional design. Well, it's no longer quite new. We've done it over the last 8 years. And we're very pleased with the results. We think we can do better again in the future, but a redesign of the functionals is a major undertaking, so we're pausing and reassessing at the moment. And there are some fundamentally difficult unsolved problems that are due to the limitations of the form of EXC that we use. And of course, there are transformational opportunities. Quantum information and non-classical computers offer maybe exciting ways around the very difficult unsolved problems. Okay, so that's that. Let me now switch to my last topic, which is a little bit different, but ultimately quantum chemistry calculations are numerical experiments, and they can yield precise results in the form of reaction mechanisms, like I showed you for CO2RR in the introduction. But they can also, if you apply them carefully, can yield chemical insight. And so I want to tell you a little bit about analysis and energy decomposition analysis in particular, because this is a method that we have been working on over quite a period, and we feel it has something to offer for problems ranging from understanding intermolecular interactions to understanding the nature of the chemical bond. So quantum chemistry normally produces energies that are referenced with respect to infinitely separated nuclei and free electrons with zero kinetic energy. All very well for calculations, not so good for analyzing those calculations. By contrast, an energy decomposition analysis tries to get to a final energy change in small steps. That is, small energy changes, not the gigantic energy changes you get from mixing a beaker of non-interacting nuclei with a second beaker of isolated zero kinetic energy electrons. So for instance, if you want to understand a chemical bond between two carbon atoms, you should begin with two methyl radicals, the same way you do when you compute the relative energy, but in fact try and do this directly in the calculation. And then a variational EDA will try and get you the lowest energy possible, subject to some physically inspired constraints that are designed to isolate different drivers of intermolecular interactions in chemical bonding. For instance, we will use a frozen trial wave function that will correspond to capturing the net result of electrostatics, dispersion interactions, and Pauli repulsions. Then we will allow electrons to rearrange on a fragment or polarize. That's induction in an intermolecular interaction. It turns out to be contraction in chemical bond formation. And then finally, let the electrons truly delocalize or charge transfer or forward and back donate or resonate from one fragment to the other to capture the final energy. And so this variational approach has the strong benefit of allowing interactions to be analyzed that are not just weak, but also as strong as chemical bonds. That should be contrasted with perturbation theory approaches. Okay, and so this is the way we currently do this is to then, I don't have time to really go through the theory, so I'll just try and sketch it in use with respect to a given chemical complex. We're going to get intermolecular interactions as the frozen energy interactions, so begin from the frozen molecular orbitals of the interacting radicals or fragments, and then allow electron rearrangement on a fragment, and then allow electron delocalization or charge transfer. And the physical content is shown here. Here's a molecule in the process of being photoionized. This is the radical cation of the glycerol molecule. So glycerol, after being photoionized, is an unhappy species and rearranges readily over a low barrier to make this triplex that consists of a water molecule down the bottom, the formaldehyde molecule at the top right, and the vinyl alcohol radical cation sitting at left. And this is stuck together, and it's a stable intermediate because of strong intermolecular interactions. The first one of those is a roughly 100 kilojoule per mole or 28 kilocalorie per mole hydrogen bond between water and vinyl alcohol radical cation, which really consists of a synergistic combination of the water molecule polarizing, the lone pair of oxygen charge transferring. Those are those energy contributions shown here. And that overcomes a repulsive frozen interaction. How can the frozen interaction be repulsive when there is a charge here and a dipole there nicely aligned? Well, the answer is because of Pauli repulsion. The hydrogen bond is only 1.4 angstroms instead of the usual 1.9 or so. So this is a very strong hydrogen bond. EDA then says that the second strongest interaction is 12 kilocalories per mole, or roughly 50 kilojoules per mole, a little less than half as strong as the strongest one. It's completely different in character, though. The interaction between formaldehyde and the other end of vinyl alcohol radical cation is dominated by the frozen interaction. In other words, the electrostatics between the dipole of formaldehyde and the charge of vinyl alcohol radical cation is 9 kilocalories per mole attractive because of the very long distance that the complex optimizes to. And because of that long distance, you can't do much polarizing of formaldehyde, and you can do very little charge transferring as well. So it's a rather different interaction. And then there's a third one, and this is a very weak, an unusually weak hydrogen bond between formaldehyde and water. It's not geometrically optimal for a hydrogen bond. It's frustrated both geometrically and electronically because this interaction must compromise because of the two much stronger ones. Anyway, so that's how EDA, how EDA is useful. You can distinguish the character of interactions. Sometimes it confirms your chemical intuition. Other times it can help develop your chemical intuition if that's lacking. We can do the same thing for chemical bonds. And so you get the same frozen, polarization, and electron delocalization terms with some differences. There's a preparation energy that I skipped over for intermolecular interactions. The preparation energy is always a geometric distortion, but for chemical bond formation, there's also an electronic distortion, which is preparing optimal hybrids for the frozen energy. And the frozen energy itself is not just the frozen MOs, but if we're making a chemical bond, it includes the spin coupling. That's the SC that you may have been wondering about up here. That's the chemical bonding with unrelaxed orbitals from the radical fragments. If you're a student of basic theories of chemical bonding, this is essentially the Heitler-London wave function. Then you can begin relaxing it, and that's the polarization energy, which includes the electric induction that we talked about for intermolecular and an orbital contraction effect that we'll talk about for a couple of minutes as we try and analyze chemical bonding here. And then finally, the electron flow between the radicals. If one is more electropositive, the other more electronegative, we get an energy number for what is this electron flow. And then in the end, you get an energy diagram. So energy on the y-axis in kilocalories per mole, and then the different contributions. The preparation energy doesn't show up for these toy chemical bonds here. There's no hybridization that's needed. There's no geometric relaxation or geometric distortion that's needed. Here is the frozen plus spin coupling energy that dominates the covalent bond between two hydrogen atoms. And then there is a significant contribution from polarization. How do two hydrogen atoms polarize each other? Well, the answer is they don't. Actually, what happens is the orbitals contract in size to satisfy the virial theorem. And we'll see this in a minute. So roughly 1/3 of the HH bond energy is this pseudo contraction or a pseudo polarization, i.e. contraction term. Things look quite a bit different in LIH, which is a polar and partly ionic interaction. You can see that the biggest single term is now the electron delocalization, and the character of polarization is now dominated by actually electrical polarization associated with preparing to charge transfer. Okay, so we can do this, and then we can try and talk. This will be my final topic, is to say a little bit about the origin of the chemical bond from this perspective. And of course, the chemical bond can be analyzed in many ways. So this is but one way of thinking about it. And so let me first summarize the conventional prevailing wisdom about the nature of the chemical bond in H2+. And this really is primarily due to the legendary theoretical chemist Klaus Rudenberg. And the plot on the right here is showing the exponent of the 1s function of the hydrogen atom on the x-axis, and on the y-axis is energy, kinetic energy, or the negative of the potential energy divided by 2. And the diamond at zeta equals 1 and kinetic energy equals 0.5 is the ground state of the hydrogen atom. That's the point at which the virial theorem is satisfied. Kinetic energy and minus a half of the potential energy balance, and the energy in the bottom plot is minimized. If we then go to look at H2+ and plot again the kinetic energy and minus a half of the potential energy, the diamond is where the energy of H2+ is minimized. But suppose you borrow, i.e. take as the frozen wave function zeta equals 1. That would then be the blue dotted line in the right-hand panels. Well, if you look at the energy and compare to the hydrogen atom, you actually get most of the way down to the binding energy. You get about 2/3 of the binding energy of H2+ just with the frozen 1s orbital of the bare hydrogen atom. And in that case, look what's happened in the upper right panel. The kinetic energy has gone down significantly. The potential energy is almost unchanged compared to the upper left panel, the bare hydrogen atom. So the picture of bonding in H2+ is that the bonding is mainly caused by delocalization or electron sharing. The one electron in H2+ is in a slightly bigger box than in the hydrogen atom. And that's 2/3 of the energy lowering. The last 1/3 is to walk on the bottom right-hand panel from zeta equals 1 to zeta is equal to about 1.25 or 1.23 to lower the energy, the last 1/3 of the way, and that's the orbital contraction. That's the 1s orbital getting a little smaller to restore the virial balance that is broken. Okay, so that's the picture. This picture was very carefully, very rigorously developed for H2 plus and H2. It has largely been presumed to transfer to other chemical bonds. With our variational EDA, we can test whether or not this presumed transference is in fact correct. Okay, so here we are now going to revisit H2 with the EDA theory for chemical bonds that I showed you. And on this slide, I'll just show you that we recapitulate Rudenberg's results. We group the frozen plus spin coupling energy. We call that the covalent energy lowering, the Heitler-London type chemical bond with the frozen orbitals of the radical fragments. And then we separate orbital contraction, and then we lump together electrical induction and charge transfer. We call that term PCT. So these are the three curves in the plot that you're looking at for total energy. And at the equilibrium bond distance of H2, we can see that we recover about at least 2/3 of the binding energy, maybe even more, just from the frozen orbital wave function. And then orbital contraction gets us most of the rest of the way. And then there is a little bit of electron delocalization, or I guess we would call it H plus H minus resonance. Small contribution between the red curve and the yellow curve. Okay, so that is that. It actually looks very similar to the Rudenberg type, kinetic energy driven chemical bond formation by extra delocalization story that I showed you on the previous slide. To confirm that's true, let's look at the kinetic energy. So now in the bottom left panel, the y-axis is kinetic energy change, and you see that the kinetic energy change for forming the frozen wave function is strongly negative, nearly minus 100 kilocalorie per mole. And then as the 1s orbitals contract, we see a very large positive increase. So that's restoring the virial balance. And so essentially this is really the same kind of picture that we saw before. All right, so that's H2. Now let's do a different chemical bond. Well, we've done a bunch of different chemical bonds, but I've only got time to show you one. So this will be a representative example, and we'll draw some general conclusions from it. You'll have to take my word that we've looked at enough other chemical bonds that these general conclusions are in fact true. So we're going to do the CC bond in butane, a simple alkane. So we'll be looking at two ethyl radicals, C3H2s, combining to make butane, and same grouping as before. And if we look at the equilibrium geometry, you can see things look broadly similar to H2. About half the energy lowering comes from the covalent wave function. That's good. And then the red curve is the energy lowering due to contraction. But wait, can you spot the red curve? It's hard to see. It's actually sitting right under the blue curve. There is almost no orbital contraction in this problem. And then finally, there is a significant amount of charge resonance or electron delocalization. That's the gap between the blue and red curves sitting on top of each other and the yellow curve that allows charge flow. So this is ethyl plus, ethyl minus, ethyl minus, ethyl plus resonance. It's relatively significant at the equilibrium geometry. As you go further out, you can sort of see that that the charge delocalization term dies away more quickly than the Heitler-London chemical bond dies away. Okay, so there's the first point, almost no energy lowering due to contraction, as I showed you. Now let's go look at the kinetic energy and confirm that everything makes sense. So the blue curve is the kinetic energy change associated with the Heitler-London wave function, and at the equilibrium geometry, it's completely different to H2. The kinetic energy goes up very much. That's why we don't get any orbital contraction afterwards, because the kinetic energy is already gone, shooting up. We get, in fact, nearly zero net change because contraction is just not energetically favorable, and we get just a tiny further increase due to electron delocalization. So this is really different. Why is it so different? In butane, the CC bond in butane compared to H2, what causes the particle in the box argument to no longer hold? Well, the most obvious thing is that the approaching sp3 orbital of the left-hand ethyl radical runs into the core electrons of the nucleus of the right-hand ethyl radical with whom it's forming a bond. So the increased kinetic energy with the Heitler-London wave function is due to increased electron confinement associated with the Pauli repulsion with the core levels that are already occupied on the other ethyl fragment, the core levels of the carbon. So the origin of the chemical bond then is the constructive interference of nearly degenerate energy levels. You've got the half-filled energy level of two ethyl radicals coming together, and the two energy level orbital diagram is the leading correct picture of chemical bond formation in butane. In H2, there is a special case that kinetic energy coincides with constructive interference. Kinetic energy lowering and constructive interference say the same thing. But in butane and in actually almost every other single bond between non-hydrogen atoms, that is also true. Okay, I'll show you, just make one or two more points. If we look at the kinetic energy change associated with forming the Heitler-London wave function, it's very repulsive at equilibrium, as you can see in the bottom left panel again. But if you stretch the bond out to about, say, oh, I don't know, let's go out to 2.2 angstroms, say, then you see the kinetic energy change has become negative. Because now we're getting out of the way of those core orbitals on the other ethyl fragment. And you can sort of see it graphically as well. Here's one ethyl fragment up the top with its sp3 hybridized. Well, it's ready to be hybridized. It's really a p-type orbital here. As we go to form the covalent bond at equilibrium, the resulting overlap of sp3 hybrids touches the core orbitals of the other ethyl radical. But if we stretch to, say, 2.2 angstroms, that Pauli repulsion is relieved, and the kinetic energy change at the bottom left panel here is negative. All right, so let's wrap up. So chemical insight from electronic structure calculations is a challenge that we have not completely met, but I've just tried to show you a bit of progress today in energy decomposition analysis and how we can use that to think about the origin of the chemical bond. Building on Rudenberg's classic analysis for H2, where the covalent bond formation is driven by, well, constructive interference or kinetic energy lowering, either is a valid picture, and that picture validly translates to other covalent chemical bonds to hydrogen. That's as far as it goes. For bonds between non-hydrogen atoms, we find the kinetic energy often increases, and this is associated with a Pauli repulsion effect. Okay, and I will stop there. Thank my co-workers, in particular Nabe for the functional work, Daniel and Yueji and Paul for the EDA, and Dip is carrying forward the functional work. And thank you for funders, and thank you for your attention. And this stuff doesn't happen without software, and so QChem 5 is the software platform we build, and this is also incorporated into the Spartan package. And thank you for listening.
Thank you very much, Professor Martin, for a very exciting talk. For reiterating again that the story of H2 plus and H2 is far from complete. There is much more to learn from the simple model systems that quantum chemists are fond of. Are there any questions now? The floor is open. So perhaps I will begin with a question. The energy decomposition analysis, which is performed using a variational approach, how does it compare with, let's say, SAPT calculations?
Yes,
I mean,
yes. So SAPT is a popular EDA for non-bonded interactions. It's an acronym for symmetry adapted perturbation theory, and it does a good job of separating what we call the frozen energy can roughly be one-to-one mapped onto electrostatics and well, where Pauli repulsion resides in SAPT, which is, I think, called exchange repulsions. The electrical induction that we speak of, or polarization, is part of the SAPT induction term, but in SAPT it is tangled up with charge transfer or electron delocalization. They don't typically separate them cleanly. And as far as I know, there is no extension of SAPT to chemical bonds as yet. But I might just make a general comment that the energy and the molecular properties of molecules are observables and are uniquely defined. The drivers of chemical bonding and non-bonded interactions are things that are only precisely defined when the interacting fragments don't overlap. And so any good theory of either chemical bond analysis or non-bonded analysis should give identical results in the non-overlapping region. And SAPT and our variational EDA, if you give them the same energy functional, I think would agree. SAPT, of course, uses its own, the results of its own perturbation theory are the answers, whereas in our EDA, we're taking a density functional and trying to decompose it. If that's the exact density functional, then in principle, our results are exact. If that is a terrible inexact density functional, then our EDA will be exact for the terrible inexact density functional. And so these energy terms are not observable. And so what we speak of as electron delocalization, well, we can only speak of it with respect to a definition. And what we speak of as orbital contraction likewise requires a definition. And reasonable scientists can disagree on the definitions. However, we believe that success will come when different complementary approaches give qualitatively the same result. And apart from the difficulty in SAPT of separating charge flow, charge transfer from induction, for non-bonded interactions, SAPT and variational EDA with a good density functional are quite compatible. Okay, maybe that's a partial answer at any rate.
Thank you. Okay, if there are no further questions, please join me in thanking Professor Martin for a very exciting talk. Thank you, Professor Martin, for having accepted our invitation to join us this evening. Thank you.
Thank you again for the invitation, and I look forward to hearing lots of exciting science coming out from the new center.
Thank you. So with this, we come to the end of the first day's events. So I hope all of you had a great time listening to a variety of talks, all woven around the theme of HPC. So let me take a minute to summarize what we have basically attempted in this first day. So we wanted to bring together expertise from various domains of mathematics, physics, biology, and chemistry, which is why we put up the series of lectures in such a way that all of them are woven around the theme of high performance computing. And I hope all of you have had a great day. We first began with Professor Keys, who talked about scalable solvers this afternoon. And then we had Professor Peter Bastian, who talked about finite element modeling simulations, both of which are more into mathematics, physics kind of backgrounds. Then we had Professor Edoardo Napoli, who talked about a bit of DFT and then the hardware architecture details and so on. Then we moved on from there to the biology applications pertaining to HPC, wherein we had Professor Bertrand talk to us about the bioinformatics aspects. So finally, in the last session, we had two speakers who spoke about high performance computing as applied to chemistry problems. We had Professor Heather Kulik talking to us about machine learning models as applied to transition metal chemistry. Finally, we had Professor Martin talking to us about the developments in density functional theory and basically telling us about energy decomposition analysis and the story of H2 plus and H2 that is far from complete today. So with this, we come to the end of the first day session. And for tomorrow, we have a hands-on session that is scheduled for 9:30 a.m. Indian Standard Time. Please use the same Zoom link to join us for the meeting. And finally, the organizing committee of High Performance Computing Center would like to take this opportunity to thank all the speakers for having taken time from their busy schedules to join us today. We would also like to thank our director, Professor Jayan Murthy, for sharing his vision for the center and for all the support that he has rendered to the center and the activities. Thank you all for joining us today. Have a great day. Goodbye.